Hey friends, welcome back. Today we're uncovering 4 secrets of the universe that will help you sleep better. Let's dive in. Jupiter is the largest planet in our solar system, but it also has the fastest spin on its axis. A day on Jupiter is shorter than 10 hours, even though its diameter is almost 103,000 kilometers. This fast rotation causes some extreme effects. For example, Jupiter is not perfectly round. It is flattened at the poles and bulging at the equator, making it almost an oblate sphere. This shape is caused by the constant centrifugal force from its rapid spinning. Before we begin further, if you genuinely like what you're watching, don't forget to hit that like button and subscribe. Also, let me know where you're watching from in the comments. I'd love to see where our amazing audience is watching from around the world. Let's begin now. This quick rotation also affects Jupiter's gravity. The gravity on the planet is not the same everywhere. At the equator, where it spins the fastest, the gravity is weaker than at the poles. This uneven distribution of gravity causes instability in its atmosphere and makes predicting its weather difficult. The high speed of rotation also makes the jet stream stronger, creating turbulent zones and bands visible even with basic telescopes. These bands are a result of the interaction between Jupiter's rotation, gravity, and its internal heat. They give Jupiter the appearance of a spinning marble. Jupiter also has a powerful magnetic field, about 20,000 times stronger than Earth's. This magnetic force comes from the rapid movement of charged particles, mainly metallic hydrogen, inside the planet. Because of this, Jupiter acts not just as a planet, but also like an incomplete star, affecting the space around it. The magnetic field extends millions of kilometers into space, protecting its moons and blocking solar radiation. Jupiter's fast rotation also influences its storms, including the Great Red Spot, a massive storm that has lasted for over 300 years. This storm is kept stable by the planet's rotating atmospheric currents. The flattened shape of Jupiter also affects the orbits of some of its moons, like Io and Europa, causing tidal forces that create enough heat to keep liquid oceans under their icy surfaces. Studying these forces helps us understand not only Jupiter, but also the way giant planets influence their entire planetary systems. Exoplanets in other systems that are similar to Jupiter show that fast rotation and strong gravity often go hand in hand. This helps us understand how these massive planets act as protectors, shaping orbits and preventing asteroids from threatening smaller planets. Rotation also leads to the formation of thin, unstable rings made of dust and captured particles. These rings are constantly influenced by Jupiter's gravity and the pull of its nearby moons. In this way, Jupiter is like a cosmic dance, with elements constantly being pulled, spun, and shaped by its rapid rotation. The planet's system behaves like a chaotic but synchronized mini-universe. Jupiter's rotation also impacts how it absorbs and reflects sunlight. Different parts of the planet get varying amounts of light, which combined with its fast spin creates intricate heat and shadow patterns. This affects everything from cloud formation to the release of infrared energy, which probes like Juno have been capturing. The planet's internal thermal energy, in combination with its fast rotation, helps keep its weather activity stable over centuries. The speed of rotation makes studying Jupiter harder. Because everything spins so quickly, probes must adjust their sensors with great precision to get clear images. This makes long-term observations difficult and forces scientists to use computational models to account for the effects of the planet's rapid movement. Even the signals sent by probes are distorted, requiring corrections when analyzing the data. Interestingly, Jupiter is becoming even more flattened. Recent studies show that its shape is slowly changing as internal processes move mass and heat around. This means that despite seeming stable, Jupiter is constantly evolving. The relationship between its rotation, gravity, and internal pressure creates a dynamic balance that challenges our understanding of planetary stability. Jupiter's gravity extends beyond just itself. It affects the orbits of nearby comets and asteroids, acting as a shield for the inner planets in our solar system. But it can also fling objects inward like a slingshot. The extreme rotation helps accentuate Jupiter's gravitational field in certain areas, making it one of the solar system's most important forces. This phenomenon is difficult to reproduce in simulations, as many computational models fail to represent the relationship between Jupiter's rotation, structure, and magnetic field accurately. Each new discovery on Jupiter forces us to adjust the scientific models we use to understand planetary physics. The extreme speed at which Jupiter spins is not just a curiosity, it is a key factor that shapes its entire system. From its weather and moons to its rings and space radiation, the way Jupiter spins affects everything around it. The Juno mission, which has been orbiting the planet since 2016, continues to provide new insights into the planet's deep winds and gravity with remarkable precision. With every new orbit, we learn more about the extreme nature of planetary rotation. By understanding Jupiter, we gain tools to study other gas giants across the universe. Neptune, despite its distance and seeming isolation, challenges our understanding of climate and thermodynamics. Its rapid changes, mysterious energy sources, and powerful winds suggest that there's still so much we don't know about how planets work. In the cold and quiet of space, this blue giant may be trying to tell us a story that we're just starting to understand. Mars has two small irregular moons called Phobos and Deimos. These moons are shaped like asteroids with dark, cratered surfaces. The mystery starts with their very existence. They don't look like Earth's moons, or the large moons of gas giants. Since they were discovered in 1807, astronomers have been puzzled about where these moons came from, and to this day there's no clear answer. The most common theory is that Phobos and Deimos are asteroids that were captured by Mars' gravity. This could explain their strange shapes and the carbon-rich composition similar to asteroids. But this theory doesn't explain why their orbits are nearly circular and aligned with Mars's equator. Normally, captured asteroids have more eccentric or tilted orbits, which raises doubts about this theory. Another idea is that the moons formed from a massive impact on Mars, like how Earth's moon was created. In this case, debris from the impact would have entered Mars's orbit and gradually formed into the two moons. This model would explain their circular orbits, but it doesn't match the moon's composition, which is different from Mars. Spectral analysis shows materials more commonly found in the Kuiper Belt asteroids. A third theory tries to combine the first two ideas. It suggests that debris from an impact might have mixed with captured asteroids, resulting in hybrid moons with stable orbits but exotic compositions. However, this idea is still just a theory, and no mission has provided direct surface data from Phobos or Deimos to confirm it. Phobos, the larger moon, is slowly spiraling toward Mars. It's gradually getting closer and is expected to either crash into the planet or break apart into a ring within the next 30 to 50 million years. This raises some questions. Why is Phobos so close to Mars and unstable, while Deimos, the smaller moon, orbits farther out and remains more stable? The differences between them suggest they might have different origins, or followed different paths of evolution. Phobos also has strange grooves on its surface. Some scientists think these grooves are caused by internal stresses, suggesting that Phobos is being stretched by Mars's gravity. Others believe these grooves could be the result of ancient impacts or fractures forming as Phobos moves closer to breaking apart. The truth is, we still don't know for sure. On the other hand, Deimos is calmer and farther away from Mars. Its surface is smoother and its orbit is more stable. But it also presents a puzzle. Why hasn't such a small moon been ejected or captured by another object over the billions of years the solar system has existed? And why does Mars only have 2 moons, while other planets like Jupiter have dozens? The Martian system seems to have been shaped by something specific. Several missions are planned to study Mars's moons. The Martian Moons Exploration Mission, MX, by Japan's JAXA, aims to land on Phobos, collect samples, and return them to Earth. This mission, scheduled for launch in 2026, could finally answer the mystery of the moon's origin. The origin of Mars' moons is also important for understanding the potential for life. If they came from outside Mars, they may have brought organic compounds or even microorganisms. If they formed from Mars, they could hold preserved samples from the planet's past. In either case, these moons are like time capsules that may offer clues about the solar system's history. These moons could also play a role in future human missions to Mars. Since Phobos and Deimos are small and have low gravity, it might be easier to establish outposts or scientific stations on them, rather than landing directly on Mars. However, understanding the moon's stability is crucial to assess the risks. Phobos, for example, may not be stable in the long term due to its decaying orbit. In the end, the mystery of Mars' moons highlights how little we know about the early days of the solar system. Phobos and Deimos are like puzzle pieces that don't fit any existing frame. Though small and seemingly harmless, they hold a secret that could change our understanding of planetary history. We've been waiting for answers for over a century, and the more we observe these moons, the stranger they seem. Their orbits, compositions, and behaviours don't match any existing models, suggesting that we may need a completely new theory to explain them. Phobos and Deimos remind us that sometimes the greatest mysteries are right in front of us, hidden in small bodies most people don't even know exist. Uranus is another strange planet with an unusual magnetic field. It rotates almost on its side, with its axis tilted nearly 98 degrees relative to its orbit. But its magnetic field is even more puzzling. Unlike Earth, Jupiter or Saturn, whose magnetic fields are aligned with their centres, Uranus' magnetic field is completely off-axis. It seems to come from a point far from the core and tilts 60 degrees from the planet's rotation axis. This misalignment causes the magnetic field to behave unpredictably as Uranus spins. Sometimes the field nearly vanishes on one side of the planet and becomes stronger on the other. This creates a magnetosphere that twists, bends, and compresses in odd ways. This behaviour is unlike anything seen on other planets in the solar system. Uranus also has a decentralised magnetic axis, which means the field isn't centred on the planet's core. It's as though a magnet were placed irregularly inside a gas ball. This results in areas of intense radiation, alternating with nearly neutral zones. Probes like Voyager 2, which flew by Uranus in NIPT-6, detected unexpected fluctuations in the planet's magnetic strength during its pass. One theory is that the magnetic field comes from a layer of conductive fluid outside the core, possibly made of suprionic water or liquid ammonia. This is different from Earth, where the field comes from a molten iron core. This electrical ocean in Uranus could be the source of its magnetic instability. But this structure is still under investigation. Uranus's magnetic field also interacts with its environment in unpredictable ways. As the planet rotates, its magnetosphere behaves like an umbrella caught in the wind. This causes irregular and localized auroras, unlike the symmetrical auroras seen on Jupiter or Saturn. These auroras are invisible to the naked eye, but can be detected with radio instruments and specialized telescopes. Another strange effect is how Uranus's magnetic field impacts its moons. Unlike other planets, where moons interact with the magnetic field in predictable ways, Uranus's moons experience varying levels of radiation depending on how the field tilts and rotates. This could affect the surface chemistry of the moons and may even cause localized climate changes. The radiation environment around Uranus is anything but stable. The magnetic field also makes it difficult to send probes to Uranus. Its unpredictable nature interferes with communications and instrument guidance, while also increasing radiation exposure risks. Any future mission to Uranus would need special shielding and precise navigation systems to handle the field's anomalies. This makes Uranus one of the most challenging destinations in the solar system. Uranus orbits the Sun slowly, taking 84 years to complete one revolution. This means its magnetic field stays under the same solar conditions for decades, which may influence how charged particles accumulate or disperse around the planet. This slow dynamic adds to the unusual behaviour of its magnetosphere, which changes over time in a non-linear way. Researchers have been modelling Uranus's magnetic field using 3D simulations, and they found that its complexity challenges existing models, suggesting that there are magnetic processes we don't yet understand. Studying Uranus could also help us understand how magnetic fields evolve on planets with non-standard internal structures, which could be useful for studying exoplanets. Uranus is a prototype for exotic planets. Despite all this, it remains one of the least explored planets. Only one probe has passed by Uranus in nearly 40 years, and scientists are calling for a dedicated mission to explore its magnetic field and internal structure in more detail. Every piece of data we collect about Uranus could reveal not just the planet's unique history, but also physical processes that have never been seen anywhere else. What seems chaotic today could actually be the key to something much bigger. Uranus teaches us that planets don't follow fixed rules. Its tilted, unstable and off-center magnetic field proves that the universe is full of exceptions. Studying Uranus isn't just about confirming theories, it's about exploring the unknown. Now, let's talk about the missing methane in Mars' atmosphere. The presence of methane on Mars has been one of the most intriguing aspects for scientists who are looking for signs of life. A large portion of methane in an atmosphere is produced by living organisms, so finding methane on Mars suggests that microbial life could exist there. It has been detected several times by orbiting instruments, Earth-based telescopes, and even NASA's Curiosity rover. But the mystery begins with how the methane levels keep changing. In 2003, ground-based telescopes detected sudden methane spikes. Then in 2009, the Mars Express probe confirmed methane in regions like Syrtis Major. Years later, Curiosity detected methane, but the levels were fluctuating wildly from one day to the next. At times, the methane disappears as if something is removing it from the atmosphere. Methane is a stable gas that should stay in Mars's atmosphere for centuries, yet it vanishes within weeks or even days. This doesn't match our expectations and suggests some unknown process is at work, destroying or removing the gas. Some scientists have suggested that chemical reactions with dust or ultraviolet radiation breaking methane into simpler compounds could explain this, but nothing has been proven for sure. Another puzzling issue is the difference in data from the ground and from orbit. While Curiosity detects methane near the surface at certain times, the Trace Gas Orbiter, which analyzes the upper atmosphere, finds no significant traces of the gas. This could mean that methane is released in very localized areas, or maybe follows a daily cycle that we don't fully understand. The gap between these measurements challenges the way we currently interpret data. One possibility is that methane could be released from underground pockets or from chemical reactions in iron-rich minerals. Mars has an ancient volcanic past, and gas pockets might still be trapped beneath its surface. These occasional releases could explain the spikes we see, but the rapid removal of methane remains a mystery. Some scientists have considered the idea that subsurface microorganisms might be producing methane in environments shielded from solar radiation, such as underground caves or permafrost. Although this theory is still speculative, it's an interesting one because most known methane sources on Earth are biological. But as of now, there's no direct evidence for this. Mars' seasons might also play a role. The yearly temperature cycle causes the soil to expand and contract, potentially cracking open to release trapped methane. This could explain some of the seasonal changes, but it doesn't account for the sudden disappearance of the gas. Current models fail to replicate this behavior accurately. Even Mars's winds, though weaker than Earth's, could have an impact. They could redistribute methane irregularly, creating spikes and dips in concentration. However, the most advanced models still fail to explain the variations we see. Mars also experiences global dust storms that last for weeks. These storms affect the atmosphere and solar radiation, possibly interfering with the methane cycle. They could speed up the breakdown of methane or block its release. But no direct link has been found between dust storms and methane events so far. To solve this mystery, the ExoMars mission was launched by ESA and Roscosmos. The Trace Gas Orbiter on this mission is equipped with ultra-sensitive methane sensors and has been collecting data since 2018. But so far, the results haven't confirmed the methane spikes detected on the surface. The discrepancy still exists, and new instruments with higher local resolution will be needed to resolve this issue. Currently, the leading hypothesis is that there are active chemical processes on Mars's surface or in its lower atmosphere that we don't yet understand. Sunlight's ultraviolet rays might be breaking down methane quickly, combined with catalytic minerals. But this theory still needs to be tested in laboratory conditions that simulate Mars' environment. The methane cycle remains one of the biggest mysteries on Mars. Now, Titan's changing atmosphere. Titan is Saturn's largest moon, and it's the only moon in the solar system with a thick, complex atmosphere. It's even thicker than Earth's atmosphere and is made mostly of nitrogen, with a significant amount of methane. What really fascinates scientists is how this atmosphere changes over time, not just with the seasons, but unpredictably. Titan's climate is unlike anything we see on Earth, and it defies conventional meteorological models. Since the Cassini probe started studying Titan in 2004, scientists have observed methane clouds forming and disappearing irregularly. These clouds don't follow a stable pattern and appear in different places each cycle. Some years see frequent storms, while others have almost none. This shows that Titan's atmosphere is more chaotic than we expected. On Titan, methane behaves like water does on Earth, evaporating, forming clouds, raining, and accumulating in lakes and seas. But over time, the amount of methane in the atmosphere and lakes seems to be decreasing. This suggests that methane is being destroyed by chemical processes or lost into space, but since no known sources are replenishing it, this remains a mystery. Titan also experiences winds that change direction depending on the altitude. The upper atmosphere rotates rapidly in one direction, while the lower atmosphere has slower or even opposite patterns. This creates vertical and horizontal instabilities that affect cloud formation and the movement of organic particles. Titan's atmospheric dynamics remain a key focus for planetary scientists. As Saturn's seasons change, each lasting about 7 Earth years, Titan's atmosphere undergoes significant shifts. When Cassini arrived, the South Pole was in sunlight, but over time it moved into darkness, while the North Pole got more sunlight. This caused wind reversals and changes in atmospheric circulation, resulting in new weather systems. In 2012, Cassini detected a strange hydrogen cyanide cloud at Titan's South Pole, which appeared rapidly and unexpectedly. Its composition suggests complex chemical reactions happening in the upper atmosphere. This kind of dynamic behavior suggests Titan's chemistry is active and responsive to subtle triggers, possibly even influenced by energetic particles from Saturn. The orange haze that covers Titan is made of organic particles called tholins, which form when ultraviolet radiation interacts with methane and nitrogen. The amount of this haze changes over time, affecting how much sunlight reaches the surface and causing unstable thermal cycles. This also influences the evaporation of methane lakes. Despite Titan's thick atmosphere, the surface pressure is only about 1.5 times that of Earth's. This pressure is enough to maintain stable liquids, but it doesn't fully explain the highly dynamic behavior seen in Titan's upper layers. Isotopic measurements of nitrogen and carbon ratios suggest that Titan might have a different origin than most of Saturn's moons, or that its atmosphere has undergone dramatic changes over billions of years. This directly affects how we understand the formation and evolution of atmospheres on icy worlds. In 2034, NASA's Dragonfly mission will arrive at Titan with a drone designed to explore different surface locations. It will directly measure atmospheric composition, record local weather patterns, and investigate the methane cycle in more detail. This mission will give us a clearer picture of Titan's mysterious and ever-changing atmosphere. In contrast, the southern hemisphere of Pluto appeared darker, more uniform, and less geologically active, though it remained mostly in shadow. Scientists were puzzled, because these differences between the hemispheres couldn't be fully explained by light or temperature alone. Even considering seasonal changes, the surface composition and texture differences were far more pronounced than expected. While Pluto's orbit and axial tilt cause extreme seasonal shifts, models suggested that the hemispheres should have relatively similar geological histories. Instead, one hemisphere seems to have undergone significant changes, while the other remains largely unchanged. One of the clearest examples of this contrast is Sputnik Planitia, the massive heart-shaped ice basin in the northern hemisphere. This area appears to be geologically active, showing signs of convection beneath its nitrogen ice crust. Meanwhile, the southern hemisphere lacks any similar features. Crater counts suggest that the southern regions are older and more heavily cratered, indicating they haven't been resurfaced recently. Spectroscopic data also show that the distribution of nitrogen, methane, and carbon monoxide ices is uneven across Pluto. These volatiles accumulate and sublimate differently between the hemispheres, but the patterns don't match solar exposure alone. For instance, some areas that should be cold traps don't hold onto volatiles, while others gather them more than expected. This suggests that subsurface processes might also influence the surface chemistry. Another hypothesis is that Pluto's internal structure or thermal history caused asymmetric resurfacing. If one hemisphere has a thinner crust or is more geologically unstable, it could lead to more cryovolcanism or tectonic activity in that region. Alternatively, past impacts might have triggered regional changes, like the redistribution of ices or localized internal heating. However, no massive impact basin has been found in the southern hemisphere yet, The southern hemisphere's darker colour might also be due to organic compounds called tholins, which are created by solar radiation interacting with methane. Tholins settle on the surface and darken over time. If the southern hemisphere hasn't experienced much atmospheric turnover or ice renewal, tholins would accumulate more easily, creating the observed darker terrain. However, this would imply a period of atmospheric stasis that models don't currently predict. Interestingly, Pluto's axial tilt causes each hemisphere to experience decades of complete darkness during its long orbital cycle. The southern hemisphere had been in darkness for over 20 years before the New Horizons flyby, which limited observational data. This makes it difficult to determine if the differences between the hemispheres are permanent or part of a slow cyclical transformation. The lack of long-term monitoring data remains a major challenge. Pluto also has a thin atmosphere that expands and contracts seasonally. This atmosphere could deposit or remove volatiles differently in each hemisphere depending on the time of year. Models suggest that during southern summer, volatile migration might replenish the northern hemisphere while the south loses material. This could help explain why the northern features appear younger, but more detailed data is needed to confirm this cycle's magnitude and mechanics. Additional mysteries involve Pluto's polar regions, especially the South Pole, which remains poorly imaged. It's unclear if polar caps exist there or if cryovolcanic activity is happening in those darker regions. The resolution of the New Horizons data wasn't high enough to capture small-scale features in the southern hemisphere, and future missions will be needed to fill in these gaps. A promising opportunity is Earth-based telescopic monitoring as Pluto re-enters more balanced solar exposure. As the southern hemisphere slowly gets illuminated again, scientists hope to observe any surface changes. This could provide critical insights into whether the features in the northern hemisphere are recent anomalies or part of broader hemispheric evolution. For now, the asymmetry between Pluto's hemispheres remains unexplained. No current theory fully explains the geological, chemical, and thermal differences between the two halves of the dwarf planet. Until another mission visits Pluto with more advanced instruments and broader coverage, the imbalance of this icy world will continue to raise questions about the dynamics of distant small planetary bodies. The internal heat source of Europa, one of Jupiter's largest moons, is another mystery that has intrigued scientists for decades. Strong evidence suggests that Europa has a subsurface ocean beneath its icy crust. Unlike most moons, Europa is geologically young and active, with very few craters and a surface marked by fractured ridges and chaotic terrain. This suggests a dynamic internal system, yet it lies far from the Sun, where solar heating alone can't account for the observed features. The source of Europa's internal heat remains one of its biggest mysteries. The most widely accepted explanation is tidal flexing. Europa orbits Jupiter in an elliptical path, influenced by gravitational interactions with neighbouring moons like Io and Ganymede. These interactions cause Europa to stretch and compress during its orbit, generating heat through friction inside its interior. This process, called tidal heating, is believed to be strong enough to maintain a subsurface ocean of liquid water beneath Europa's ice shell. However, recent data suggests that tidal heating alone might not explain everything. Models indicate that the heat produced might not be enough to keep the global ocean stable over billions of years unless there are additional energy sources. One possibility is radioactive decay within Europa's rocky mantle. If Europa has a differentiated interior with silicate rock and metallic layers, natural radioactivity could produce significant internal heat over geological timescales. Another mystery is the thickness and behaviour of Europa's ice shell. Some models suggest that it might be as thin as 10 kilometres in some areas, while others propose a much thicker crust. Observations from the Galileo spacecraft showed signs of potential chaotic terrain, where ice blocks appeared to have broken apart and rotated, possibly floating on a liquid subsurface layer. These formations suggest that heat is being transferred from below in ways that are not yet fully understood. There are also signs of recent geological activity, such as plumes of water vapour detected by the Hubble Space Telescope. These plumes may be geysers ejecting water vapour or ice particles into space, which could provide direct access to the subsurface ocean, offering clues not only to the heat source but also to Europa's potential for hosting life. Europa's surface also shows evidence of resurfacing due to upwelling materials. Areas of rigid plains and discoloration could result from warmer ice or brine pushing up from beneath, indicating convection or partial melting. This requires sustained heat from below, possibly delivered in pulses rather than steady flows. The frequency and patterns of such upwellings are still being studied, but they suggest a more active interior than previously thought. Magnetic field measurements taken by the Galileo spacecraft revealed an induced magnetic field around Europa. This is interpreted as evidence of a salty, electrically conductive ocean beneath its surface, further supporting the idea of internal heating to keep the water in liquid form. However, the field strength and variability suggest that the ocean isn't just present, it may be circulating actively, which again points to internal energy at work. Europa's interior may even experience hydrothermal activity at the ocean floor. If its rocky mantle interacts with water like Earth's deep-sea hydrothermal vents, this could generate localized hotspots, which are considered potential habitats for microbial life. But direct evidence of such systems remains out of reach for now. The upcoming Europa Clipper mission, set to launch in the late 2020s, will investigate these questions in unprecedented detail. Equipped with ice-penetrating radar, thermal imaging, and spectrometers, it will measure ice thickness, look for active plumes, and map temperature variations. This data will help determine where the heat is coming from and how it's distributed throughout Europa's interior. The combination of tidal, radioactive, and possibly hydrothermal heating mechanisms makes Europa one of the most geologically complex objects in our solar system. Understanding how these forces interact could reveal how small icy worlds remain active over billions of years and whether they might harbour life. Europa is more than just a cold, distant moon. It's a dynamic system driven by internal energy sources that we still don't fully understand. Unlocking the origin and mechanics of Europa's internal heat could provide broader insights into the evolution of ocean worlds, not just around Jupiter, but also around exoplanets and moons across the galaxy. Europa remains a top target for exploration, offering answers to questions that link planetary science, geology, and astrobiology in one icy package. However, the planet shows no obvious signs of a massive collision, like a large moon or significant surface damage. The second theory involves atmospheric tides. Venus has an incredibly thick atmosphere made mostly of carbon dioxide, with surface pressure 92 times that of Earth's. The atmosphere spins much faster than the surface, a phenomenon known as superrotation. Some scientists believe that over billions of years, the interactions between Venus's thick atmosphere and its surface may have gradually slowed down and even reversed the planet's spin direction. This slow backward spin has major effects on Venus's climate and structure. A day on Venus lasts 117 Earth days because of the interplay between its rotation and orbit. This creates extreme temperature patterns and long sunrises and sunsets. Interestingly, despite its slow spin, Venus has hurricane-speed winds in the upper atmosphere that circle the planet in just a few Earth days. This slow spin also means Venus doesn't have a strong magnetic field. Planetary magnetic fields are usually created by movements of molten metal in a planet's core, but Venus's sluggish rotation may be too weak to generate a magnetic field. Without one, the planet's atmosphere is vulnerable to being stripped away by solar wind. Still, Venus keeps its thick atmosphere, which raises questions about how it has managed to retain it for such a long time. Simulations have been used to try to recreate Venus's rotational history, but the results vary depending on the starting conditions. Some models suggest Venus might have had a regular prograde spin for billions of years before slowly reversing due to complex gravitational interactions with the Sun and its own atmosphere. Others propose that Venus has always been different, with its slow spin being a natural result of its close proximity to the Sun. The retrograde rotation also makes landing and navigating spacecraft difficult. Missions have to approach Venus from unusual angles and account for the planet's reverse surface motion. Venus's thick clouds make it hard to observe the surface, so most of what we know about its rotation comes from radar and spacecraft flybys, like those from the Magellan and Akatsuki missions. Some researchers think that Venus's current rotation might not be stable in the long term. If atmospheric dynamics keep interacting with the surface and solar tides, Venus's spin rate could change again. Over incredibly long timescales, Venus could speed up, slow down further, or even flip again depending on how the forces balance out. The contrast between Venus and Earth is especially striking because the two planets are similar in size, composition, and distance from the Sun, yet Venus has become a radically different world. Its backward spin is a strong reminder that even small differences in a planet's early history can lead to dramatically different outcomes over time. Future missions like NASA's Veritas and ESA's Envision will help map Venus's surface and study its interior. These observations may give us new insights into why Venus spins the way it does. Understanding Venus's rotation is not just about curiosity. It's crucial to understanding how terrestrial planets develop their atmospheres, climates, and geological activity. Mercury, the smallest planet in our solar system, has a magnetic field, but it's not what scientists expected. Discovered by the Mariner 10 mission in 1974, Mercury's magnetic field is weak, only about 1% as strong as Earth's. The real mystery is its asymmetry. The field is stronger in Mercury's northern hemisphere than in the southern, an imbalance that hasn't been seen on any other planet. This oddity continues to puzzle scientists. Normally, planetary magnetic fields are aligned with a planet's core, but Mercury's magnetic field is shifted about 20% of the planet's radius northward. This means the magnetic field lines are more concentrated above the northern hemisphere, while the southern hemisphere has a weaker magnetic field. No one knows why this displacement occurs. Planetary magnetic fields are generated by the movement of conductive fluids, usually molten iron, inside a planet's core. Mercury, despite being small and cooling rapidly, still has a liquid outer core. However, models predicted that the dynamo should have stopped a long time ago. Its persistence and asymmetry suggest an unusual internal structure or mechanism. One theory is that Mercury's core might be compositional, with a solid inner core surrounded by a liquid outer layer. If the motion of the fluid isn't uniform across the core, the magnetic field could become lopsided. However, this idea needs seismic data to confirm, which we don't have for Mercury. Another explanation involves Mercury's mantle. The planet has a relatively thin rocky shell compared to its huge metallic core. If heat flow within the mantle is uneven, it might affect convection patterns inside the core, causing the magnetic field to favour one hemisphere. This idea fits with some models of Mercury's thermal evolution, but remains speculative without detailed heat flow data. The Bepi-Colombo mission, launched by ESA and JAXA, is on its way to Mercury and will provide high-resolution magnetic and geological data when it arrives in 2025. It will be equipped to detect subtle variations in the magnetic field, test dynamo models, and potentially locate the boundary of the inner core. This data could offer insight into the cause of Mercury's lopsided magnetism. Mercury's magnetosphere behaves differently from Earth's. Because Mercury is so close to the Sun, the solar wind compresses its magnetic field into a narrow, distorted shape. This makes the magnetic offset even more significant, as one hemisphere gets more protection than the other. This also creates unique patterns of particle precipitation and auroral activity. The weak magnetic field also affects Mercury's exosphere, a thin cloud of atoms released from the surface by solar radiation. Variations in the magnetic field affect how particles like sodium and potassium are transported and lost into space. Understanding this interaction is key to understanding how Mercury has evolved under such intense solar exposure. Despite its small size and proximities to the Sun, Mercury's magnetic complexity is on par with much larger planets. The field not only shifts but also varies over time, suggesting that Mercury's core is more dynamically active than once thought. These fluctuations challenge our existing theories about planetary magnetism and show that even planets once thought to be geologically dead can surprise us. As data from Bepi-Colombo arrives, we may need to update our models of how planetary dynamos work, especially in smaller metal-rich worlds. Mercury could serve as a key to understanding magnetism in exoplanets too. In September 2020, an international group of astronomers announced the detection of phosphine, pH3, in Venus's atmosphere. On Earth, phosphine is a rare molecule usually produced by biological processes in anaerobic environments. The discovery of phosphine on Venus, a planet with extremely high temperatures and acidic clouds, was a major surprise. It sparked speculation that microbial life could exist within the planet's upper layers. Phosphine was detected using spectroscopy at the James Clerk Maxwell Telescope and later confirmed with the ALMA radio telescope. The concentration was about 20 parts per billion, a level that couldn't be easily explained by known chemical processes on Venus. Computer models ruled out volcanic emissions, lightning strikes, and photochemical reactions as sufficient explanations. The most interesting possibility is that microorganisms might be living in the upper cloud layers, where temperatures are less extreme and atmospheric pressures are similar to Earth's sea level. However, Venus's clouds consist almost entirely of sulfuric acid, making the environment extremely hostile. Any life forms would need remarkable biochemical adaptations to survive. The discovery quickly sparked controversy. Subsequent research teams reanalyzed ALMA's data and suggested possible calibration errors that could have influenced the initial findings. When these errors were corrected, the phosphine signal appeared weaker or even absent. Despite the reduced phosphine levels, explaining its presence on Venus without unconventional sources remains difficult. This controversy has renewed interest in missions aimed at studying Venus's atmosphere. NASA and ESA have planned missions such as Da Vinci and Veritas to study Venus's chemistry and geology in more detail. Venus has shown other unusual atmospheric anomalies like unexplained ultraviolet absorbing particles. Some scientists speculate that these patterns might be the result of biological processes or unusual mineral reactions. The idea of a cloud-based biosphere is gaining attention again, but it remains speculative. It's important to note that finding phosphine doesn't prove life exists. It can also be produced industrially or by certain microbes. But it's possible that Venus has unknown geological mechanisms that could generate it. Gas giants like Jupiter also produce phosphine at extreme depths, under high pressure, a scenario that seems unlikely for Venus due to its structure. Venus may have once been a more temperate planet, potentially supporting liquid water on its surface. If life existed back then, some organisms might have migrated or adapted to survive at higher altitudes where conditions were less extreme. While this is speculative, it remains a plausible idea in astrobiology. Additionally, phosphine rapidly breaks down in Venus's atmosphere due to solar radiation and reactions with oxidizing compounds. So if phosphine truly exists, it must be constantly replenished by active biological or geological processes. This need for a continuous source adds to the mystery of its potential presence. The debate about phosphine on Venus is still ongoing, with research continuing since 2020. The scientific community remains divided, with some being skeptical and others cautiously optimistic. This situation highlights the importance of direct investigations using atmospheric probes capable of in situ measurements. Until then, Venus remains one of the most intriguing targets in the search for extraterrestrial life. For decades, astronomers have observed small discrepancies in Neptune's orbit compared to what traditional gravitational models predict. These variations suggest that something is gently but continuously influencing the planet's motion. This anomaly was first noticed in the 19th century, when similar irregularities in Uranus's orbit led to the discovery of Neptune in 1846. Now, Neptune seems to be experiencing similar interference. This anomaly has sparked renewed interest in the possible existence of a ninth planet, often called Planet 9 or Planet X. According to this theory, a massive, as yet undetected object could be orbiting the outer reaches of the solar system beyond Pluto. Its gravity could be subtly affecting Neptune's orbit, as well as the orbits of other trans-Neptunian objects. Models suggest that if this planet exists, it could be 5 to 10 times the mass of Earth and located hundreds of astronomical units away from the Sun. The gravitational pull of this hypothetical planet wouldn't drastically alter Neptune's orbit, but it could cause a gradual precession over millions of years, explaining the subtle deviations that have been detected in precise measurements. Objects beyond Neptune in the Kuiper belt have also shown unusual orbital behaviors, such as unexpected inclinations and non-random alignments. An unseen massive object could potentially explain these anomalies. However, no telescope has directly detected this proposed planet yet. Alternative explanations include errors in the gravitational models used to predict Neptune's position, or uncertainties about the mass of other planets and distant objects. There could also be lingering effects from galactic tides or gravitational perturbations caused by nearby stars during the early formation of the solar system, subtly influencing Neptune's orbit. Modern measurement precision has improved significantly thanks to space observatories like Gaia and radio telescopes that track planetary positions with extreme accuracy. These tools have refined our understanding of orbital dynamics, but Neptune's anomaly still presents a small but consistent discrepancy between theory and observation. While Neptune's orbit is stable over short timescales, long-term simulations show cumulative deviations. This suggests a weak but continuous gravitational influence. A distant, massive object with a slow elliptical orbit could produce such interference over hundreds of millions of years. If Planet 9 does exist, its discovery would dramatically reshape our understanding of the solar system's structure and scale, and could prompt a revision of planetary formation models. On the other hand, if the anomaly is ultimately explained by known physics, that would still advance our knowledge, particularly in how we model gravitational interactions in complex systems. Some astronomers have speculated that the anomaly might be linked to local dark matter, though this idea remains highly speculative. Dark matter is generally considered a galactic-scale phenomenon, but some theories suggest small concentrations of it could exist within the solar system, subtly influencing the outer planets. However, this hypothesis lacks direct observational support. Future missions to study the outer solar system may help resolve this mystery. A proposed NASA mission called the Interstellar Probe would include gravity and position measurements as it exits the solar system. It could directly detect gravitational deviations and help confirm or dismiss the presence of hidden masses. The search for answers continues on the frontier of what we know. The far side of the Moon, which never faces Earth, has long been shrouded in mystery due to its isolation and inaccessibility. For years, little was known about this region. It was first observed in 1959 by the Soviet Luna 3 probe and has since been the focus of various scientific missions. In the 21st century, it gained renewed intrigue with the detection of low-frequency radio signals originating from this region. In 2018, China's Chang'e 4 mission successfully landed on the Moon's far side and brought a small radio telescope aboard the Queqiao relay satellite. The goal was to detect ultra-low-frequency radio signals, which are typically blocked by Earth's atmosphere and drowned out by electromagnetic noise. The far side of the Moon provides a unique advantage. It is completely shielded from Earth's transmissions when facing deep space. During these observations, scientists picked up natural radio emissions known as Type 3 solar radio bursts, which are associated with solar flares and charged particles traveling through space. While these waves were already known, capturing them in such a quiet environment revealed subtle details that had never been observed before. However, some signals detected couldn't be immediately identified, sparking speculation about their origins. A few of these signals had characteristics such as irregular pulses and unusual dispersion, leading researchers to consider poorly understood phenomena related to solar wind or even distant cosmic events. So far, there's been no concrete evidence pointing to artificial or extraterrestrial sources, but the signals were significant because they were captured in an unprecedented setting on the Moon. Additionally, studies suggest that the Moon's far side could one day host large-scale fixed radio telescopes. Such installations could detect signals from the early universe, especially from the cosmic dark ages, before the first stars formed, signals that are undetectable from Earth due to interference. The surface of the far side is also geologically different from the near side. It has more craters and fewer basaltic lunar seas, suggesting a different evolutionary history. This supports the idea that the far side could offer new insights into the Moon's origins, and even the early history of Earth. Analysing its composition might reveal ancient internal layers that have been preserved due to the lack of recent volcanic activity. Another intriguing discovery by the Chang'e 4 mission was the detection of underground anomalies using radar. Some subsurface layers reflected signals in unusual ways, suggesting structures possibly caused by ancient impacts or unexpected lava flows. While not directly related to the radio signals, these formations have sparked further scientific interest in the region. In astrobiology, the far side of the Moon also offers an environment less exposed to direct radiation from Earth and the Sun, making it ideal for experiments that need minimal interference. One idea is to deploy biosensors to study how organic compounds behave in such isolation and whether complex molecules could form or survive under these conditions. There's also been discussion about detecting faint technological signals from distant exoplanets. With near total radio silence, a lunar radio telescope could be sensitive enough to pick up weak transmissions from hypothetical civilizations. For now, this remains speculative, but the technical feasibility is actively being explored by scientists and space agencies. While these mysterious signals don't necessarily indicate anything extraordinary, they highlight the strategic importance of the Moon's far side for cutting-edge science. Continued missions to this region could usher in a new era of radio astronomy, offering a clearer, deeper listening post to explore the universe from a surface that was once almost completely hidden from view. The unexpected acceleration of the Pioneer probes in deep space is another mystery. NASA's Pioneer 10 and 11 spacecraft, launched in the 1970s, were the first human-made objects to travel beyond the gas giants of our solar system. As they journeyed into interstellar space, both probes experienced a small but persistent acceleration directed back toward the Sun. This acceleration, approximately 8.74 ms2, was subtle but measurable. The anomaly was detected through precise Doppler measurements of the radio signals transmitted by the probes. For years, scientists puzzled over what could be causing this small trajectory deviation. Initially, they suspected instrument errors or miscalculated gravitational effects, but after thorough reviews of the data, no definitive explanation was found. Early hypotheses included the influence of dark matter, modifications to gravity at large distances, or even unaccounted relativistic effects. Some theories even proposed that new laws of physics might be needed to explain the spacecraft behavior in regions where the Sun's influence should be negligible. The so-called Pioneer anomaly became one of the most debated mysteries in modern astronomy. Another investigative angle focused on the design of the probes themselves. Both probes were equipped with radioisotope thermoelectric generators, RTGs, which emitted heat unevenly. Scientists began to consider that this uneven heat emission might act as a form of microthrust. Essentially, the probes could be pushed slightly by the heat they emitted. Refined thermal models were developed using old mission data and advanced computer simulations. After more than a decade of analysis, a 2012 study concluded that the asymmetric thermal radiation explained almost all of the observed acceleration. Heat reflected off the spacecraft's metallic structures created a small continuous thrust that was enough to account for the anomaly. Still, not everyone was fully convinced. Some argued that the thermal model relied on uncertain parameters and that minor discrepancies remained. The scientific debate continued for several years, serving as a classic example of how unexpected phenomena can reveal gaps in engineering or our understanding of known physics. The Pioneer case also influenced planning for future interstellar missions. It emphasized the need for more accurate thermal models and sensitive navigation systems to prevent misinterpretation of trajectory data. Missions like New Horizons and the upcoming Interstellar probe have incorporated lessons learned directly from the Pioneer experience. Pioneer 10 was the first spacecraft to cross Neptune's orbit and is now drifting toward interstellar space. Pioneer 11 flew past Jupiter and Saturn before eventually losing contact. Both remain milestones in the history of space exploration and examples of how even small, seemingly trivial details can spark profound discussions about the nature of the universe. The Pioneer anomaly didn't uncover new physics, but it offered something equally valuable, a reminder of the importance of accounting for all physical effects, no matter how subtle, in space missions. Ultimately, the acceleration appears to have been caused by a very earthly phenomenon: heat. Yet its discovery required years of observation, international collaboration, and scientific rigor. Today the probes are silent, drifting endlessly toward the stars. The legacy of the anomaly they sparked endures as a testament to how even the quietest corners of space can surprise us until science finds the answer. The WOW signal, a possible extraterrestrial message from 1977, remains one of the most iconic events in the search for extraterrestrial intelligence. On August 15, 1977, astronomer Jerry R. Amon was analyzing data from Ohio State University's Big Ear radio telescope when he saw a signal so unusual that he circled it and wrote "Wow" in the margin. That simple note became the name of this mysterious event. The signal was incredibly strong, narrowband, and had precise characteristics that made it stand out from typical background noise. It lasted for 72 seconds and came from the direction of the constellation Sagittarius. Its frequency was 1420 MHz, which is exactly the hydrogen line, a naturally quiet frequency that many believe would be ideal for interstellar communication. Hydrogen is the most common element in the universe, making its frequency a logical universal standard. The precision of the frequency suggested it wasn't random noise. No known astronomical object or natural phenomenon could explain all the signal's characteristics. It wasn't a pulsar, quasar, or satellite. The telescope was fixed, so the signal's duration aligned with the Earth's rotation, a strong indication that it came from a fixed point in space. The 72-second length exactly matched the telescope's sweep time across any point in the sky. Efforts were made to redetect the signal, but despite multiple observatories and researchers pointing their instruments at the same region in Sagittarius, the signal was never heard again. This lack of repetition is one of the key reasons why the WOW signal remains unexplained and unconfirmed. For a signal to be considered a candidate for intelligent origin, reproducibility is critical. Some suggested that it could have been a military or communication satellite, but none were known to be in that region or at that frequency. Others speculated that a passing comet might have emitted radio wave at 1420 MHz. In 2017, a study claimed that Comet 266P Christensen could have been in the right location at the time. However, this explanation has been widely debated and lacks strong evidence. The strength of the signal was another unusual factor. It spiked at over 30 times the background noise, something rarely seen in natural sources. It also had a clear start and end, not fading in and out as would be expected from most cosmic emissions. This abruptness suggested an artificial origin, or at least one with a unique mechanism. The narrow bandwidth of the signal was also striking. Most natural sources emit across a wide range of frequencies, but the WOW signal was sharply focused like a radio transmission. Narrowband emissions are a classic indicator in SETI, Search for Extraterrestrial Intelligence searches, as they are uncommon in natural processes. This made the signal even more compelling to researchers. Over the decades, the WOW signal has become a cultural reference point for the possibility of alien contact. It's often cited in documentaries, books, and science fiction as one of the most credible non-natural detections. Yet despite the fascination, its single appearance makes it scientifically elusive. Scientists remain cautious about drawing firm conclusions. Technologically, our capabilities have vastly improved since 1977. Modern radio telescopes like the Allen Telescope Array and FAST have much higher sensitivity and real-time data processing. Yet none have replicated anything quite like the WOW signal from the same region or at the same frequency. This only deepens the mystery. If it were a regular cosmic source, it should have reappeared. One lingering possibility is that it was a deliberate signal, a one-time beacon sent in our direction by chance or design. If such a transmission were highly directional and brief, we may have simply passed through it for those 72 seconds and then lost it forever. This would fit with the idea that some civilizations might use interstellar pings instead of continuous broadcasts. To this day, the WOW signal has not been definitively explained. It remains the best single candidate for a non-natural, possibly intelligent source of radio waves ever detected. But the absence of repetition prevents it from being categorized as proof. It remains in the delicate space between anomaly and revelation, a question that has endured for nearly half a century. Whether it was a cosmic fluke, a lost signal, or the first whisper from beyond, the WOW signal continues to inspire curiosity. It serves as a reminder that even among vast data streams, a few seconds of something truly different can shake our assumptions. Until we detect it again, or something like it, the mystery remains open. Fast radio bursts, FRBs, are brief, powerful pulses of radio waves coming from distant parts of the universe. First discovered in 2007 through archival data, these bursts last only milliseconds but release as much energy as the sun does in a full day. Their origin remains one of the most perplexing modern astronomical mysteries. To date, hundreds have been detected, many from billions of light-years away. Their short duration makes them difficult to study. They appear suddenly without warning and are often gone before telescopes can focus on them. Some FRBs have been observed only once, while others, like 111102, repeat on unpredictable schedules. The existence of repeating FRBs suggests that more than one type of source may be involved. Various theories have been proposed to explain their origin. Some suggest they come from highly magnetized neutron stars called magnetars. Others propose links to black hole activity, supernova remnants, or even cosmic strings. However, no single model can explain the wide range of behaviors observed, especially the repeating bursts with regular or irregular intervals. One particularly strange discovery was FRB 916, which repeats every 16.35 days. This kind of periodicity hints at a binary system or orbiting body affecting the burst timing. However, even in these repeating cases, the mechanism creating such high-energy bursts remains unknown. No known natural process produces radio pulses of such intensity and brevity across such vast distances. FRBs often show a property called dispersion. Their signals arrive at Earth stretched out over time, with lower frequencies arriving slightly later than higher ones. This indicates the signals have travelled through vast amounts of intergalactic plasma. From this, scientists can estimate the distance to the source, sometimes billions of light years away, which only adds to the mystery. Some FRBs exhibit polarization, a twisting of their radio waves as they pass through magnetic fields. This suggests that they might originate from regions with intense magnetic environments, like those near black holes or magnetars. However, the exact cause of this polarization is still under debate. No two FRBs are exactly alike, which makes it difficult to form a unified explanation. In rare cases, some FRBs have been traced back to their host galaxies. In 2020, an FRB-like event was observed within our own galaxy for the first time, tied to a known magnetar. This discovery provided the strongest evidence so far that some FRBs originate from these exotic neutron stars. However, the energy of this event was much lower than that of extragalactic FRBs, raising questions about the scale of the phenomenon. The idea that FRBs could be artificial has been suggested, but it remains speculative. For now, scientists continue to investigate the origin of these mysterious bursts, hoping to uncover the secrets they hold about the universe. Some researchers have suggested that alien civilizations might use focused radio bursts to power light sails or communicate across space. These ideas are interesting but lack concrete evidence. Most scientists prefer natural explanations, although they admit that the data doesn't fully align with any known mechanisms. The detection of FRBs has accelerated thanks to telescopes like CHIME in Canada, which has discovered hundreds of bursts due to its wide field of view. CHIME can monitor large areas of the sky continuously, making it perfect for spotting transient phenomena. It has helped identify new repeating bursts and provided statistical patterns that are beginning to shape theoretical models. However, FRBs remain unpredictable. They can appear anywhere in the sky at any time, without clear warning signs. This randomness makes targeted observation difficult and limits our understanding of their origins. Even with modern data collection, most FRBs are detected after the fact, leaving only brief traces to analyse. The sheer energy and frequency of FRBs suggest they might be common events on a cosmic scale. Yet their discovery is recent, and our sample size is still small compared to what likely exists. As detection methods improve, astronomers expect to catalogue thousands more, which could finally reveal patterns in their origin and behaviour. For now, FRBs remain one of astronomy's most exciting frontiers. Fast, fleeting messages from deep space with unknown senders and cryptic content. Whether they come from dying stars, colliding objects, or something more exotic, they remind us that the universe still holds surprises far beyond our expectations. In 2015, astronomers analysing data from the Kepler Space Telescope discovered a star behaving in an extraordinarily unusual way. Catalogued as KIC 8462852, it became popularly known as Tabby's star, named after astronomer Tabitha Boyer-Gian, who led its investigation. The star's brightness would drop erratically, sometimes by as much as 22%, in patterns unlike anything previously observed. While stars can dim when planets transit in front of them, this didn't follow the usual pattern. A planet passing in front of a star typically causes a smooth periodic dip in brightness. But Tabby's star displayed deep, irregular and non-cyclic dips, ruling out simple explanations like planets, moons, or even complex planetary systems. The variations lasted days or weeks and didn't repeat on any fixed schedule. One of the earliest hypotheses suggested clouds of dust orbiting the star, partially and randomly blocking its light. These clouds could come from comets or asteroids breaking apart. However, the sheer amount of dust needed to cause such dramatic dimming made this explanation unlikely without further evidence. A more radical theory proposed the presence of an artificial megastructure, like a partial Dyson sphere, built by an advanced civilization to harvest stellar energy. While highly speculative, this idea drew both scientific and popular interest, mainly because no natural explanation initially fit the data. Even efforts to monitor the star for radio signals didn't produce any evidence. Further studies showed that the dimming was more pronounced in blue wavelengths than in infrared, indicating the light was being blocked by very fine dust particles. Larger particles would block all colours more evenly. This finding strengthened the dust theory, but the origin of the dust remained a mystery. One idea proposed that fragments from a destroyed planet or moon were orbiting the star on an elongated path, spreading out and intermittently blocking the light. But such an event would be rare, and catching it in action would be statistically unlikely. Other scientists suggested a debris cloud in an inclined, eccentric orbit, possibly caused by ancient collisions in the system. This cloud could be denser in certain areas, causing temporary dimming when passing in front of the star. Though plausible, this scenario requires a very specific and unusual orbital configuration. Some long-term observations also showed that the star has been gradually dimming over decades, a slow fade that differs from the abrupt dips. This might point to deeper stellar processes, possibly involving changes in the star's energy output. However, the star's spectral type doesn't predict this kind of behaviour. Tabby's star is an F-type star, slightly larger and hotter than the Sun, and stars of this type typically don't exhibit this level of variability. This only adds to the mystery. Scientists have monitored other similar stars, but none have shown the same combination of sudden dips and long-term dimming. Currently, the most widely accepted explanation involves asymmetrical complex dust patterns, possibly combined with stellar activity or undiscovered rings of orbiting bodies. Still, there's no definitive consensus. The mystery continues as each new observation introduces variations that challenge existing models. The scientific community continues to monitor Tabby's star using optical and infrared telescopes, with citizen science projects contributing constant data. The hope is that over time, the patterns will become clearer and lead to a concrete explanation. For now, it remains one of the most baffling stars ever observed. Despite many theories being ruled out or revised, Tabby's star stands as a real-world example of how the universe can behave in completely unexpected ways. It reminds us of the value of keeping an open mind in science. With rigor and patience, its strange flickers have yet to give up all their secrets. In 2023, astronomers announced the detection of the most powerful explosion ever recorded in the universe, known as AT21LWX, occurring 8 billion light-years away. This explosion was so intense it outshone any supernova ever observed, estimated to be up to 100 times more energetic. It lasted more than 3 years, far exceeding the typical lifespan of supernovae or stellar mergers. The event was detected by several observatories, including the Zwicky Transient Facility, ZTF, and ATLAS, both specialized in spotting temporary cosmic phenomena. At first, astronomers thought it might be a slow supernova, or an unusual stellar merger. However, the energy output was far beyond what any known star collapse model could explain. Analysis suggested the explosion was caused by a supermassive black hole consuming a massive cloud of gas, equivalent to thousands of suns. This process, known as extreme accretion, unleashes colossal amounts of energy as the material is heated and accelerated before crossing the event horizon. It's like feeding a cosmic monster until it glows brighter than entire galaxies. What made AT21LWX even more unusual was its prolonged brightness. Supernovae typically peak in a few weeks and then fade, but this event remained luminous for over 1,000 days, indicating a continuous energy source rather than a single explosive burst. Instead of a flash, it resembled a drawn-out feast of gas being gradually devoured. Spectral analysis revealed highly ionized hydrogen, evidence that the original gas was dense and rich in primordial matter. This detail supports the idea that the black hole consumed a massive chunk of a galactic disk or even an entire molecular cloud. The violent interaction produced shock waves and radiation that travelled billions of years before reaching Earth. Surprisingly, the explosion wasn't noticed right away. It went undetected for nearly 2 years because it occurred in a poorly monitored region of the sky. Only by revisiting archival data and comparing photometric surveys did astronomers reconstruct the beginning of the blast. This suggests similar events might be happening right now, unnoticed. Originally labelled ZTF-20AB, the event was later renamed AT21LWX to reflect its magnitude. It's about 10 times brighter than the neutron star merger observed in 2017, and more enduring than any known supernova. This discovery redefines what we consider possible in terms of cosmic energy output. Despite involving a black hole, the light we see didn't come from the black hole itself. It came from the material swirling around it. As the gas spiraled inward, extreme gravitational forces heated it to the point of radiating vast amounts of energy. This process is so efficient it converts a significant portion of mass into pure energy, in line with Einstein's famous equation. Astronomers are now combing through old telescope archives in search of similar phenomena. The goal is to determine whether AT21LWX was a one-of-a-kind outlier or part of a rare but recurring class of cosmic events. Its discovery hints that black hole activity might be even more violent and varied than previously imagined. Future missions like the Vera C. Rubin Observatory and the James Webb Space Telescope are expected to detect such events more quickly and in greater detail. These tools could uncover more of these cosmic monsters hiding in remote corners of the universe, opening a new window into the physics of supermassive black holes. The origin of the gas cloud devoured by the black hole remains unclear. It may have resulted from a galactic collision, a gravitational disturbance, or an unstable accretion disk. Each possibility carries different implications for how large-scale cosmic structures form and evolve. Beyond its sheer spectacle, AT2021LWX could help unlock fundamental questions in astrophysics. With its extraordinary brightness and unprecedented duration, AT21LWX has already earned its place in astronomical history. It not only shattered known limits of cosmic explosions, but also marked a new frontier in observing extreme events. Even after billions of years travelling through space, the universe still has the power to astonish. In January 2022, Australian astronomers announced the discovery of a periodic radio source within our own galaxy. This unprecedented and puzzling find was named GLEAM XJ-WAX2759.52350.4.3. The source emits intense radio pulses every 18 minutes, an unusually long interval for any known celestial object. The discovery was made using the Murchison Wide Field Array Radio Telescope in Western Australia. The signal stood out for its precise regularity and strong intensity, traits typically associated with pulsars. However, pulsars spin much faster, producing pulses in milliseconds or seconds. An 18-minute interval was well outside the expected range, immediately ruling out the most common candidates. This led scientists to believe they were witnessing a new class of astrophysical object. In addition to its periodic nature, the signal was polarized, indicating it had passed through a powerful magnetic field. This suggests a compact stellar origin, such as a magnetized white dwarf or an unusual type of neutron star. Yet none of the known categories fully explain the observed behavior, turning the object into a genuine cosmic mystery. For 3 weeks, the signal appeared and disappeared with near perfect consistency, then it vanished entirely. Since then, astronomers have been unable to detect it again, even with highly sensitive instruments. This adds to the mystery and suggests it may be a transient or intermittent phenomenon, only active for brief periods. One leading hypothesis is that the object could be a slowly rotating magnetar, a neutron star with an extremely intense magnetic field, but with an unusually long rotation period. Previously discovered magnetars all spin much faster. If confirmed, this would expand the known range of neutron star properties. Still, the 80-minute cycle remains difficult to reconcile with existing models. Scientists also explored the possibility of orbital instabilities in a binary system with interacting material, which could produce cyclic radiation pulses as matter crosses certain regions. However, the strict regularity and sudden disappearance don't fit well with this scenario. The data show no orbital variations or multiple sources. Triangulation and signal dispersion analysis confirmed the source is within the Milky Way, about 4,000 light-years from Earth, relatively nearby in galactic terms. This proximity makes it an ideal target for future observations should it become active again. The exact periodicity suggests a highly stable physical mechanism. Cosmic periodic events are usually linked to rotational orbits, but no simple model combines slow rotation, intense radio emission, and polarization in a single object. As a result, scientists are considering the possibility that this could be a previously unknown type of stellar remnant. Since the discovery, other radio telescopes, including CHIME and MEERKAT, have been enlisted to search for similar signals in different parts of the sky. The hope is to find more objects with unusual periodicity, which could help establish a new astrophysical category. For now, GLEAM XJ-WEX-275 remains unique and enigmatic. The signal's disappearance has also sparked more exotic theories. Some have speculated about artificial transmissions given the signal's regularity and polarization, traits often targeted by SETI programs. However, the astronomers behind the discovery dismissed this idea, citing a still unknown but natural astrophysical origin. This case underscores the importance of continuous sky monitoring, especially in underexplored radio frequencies. Transient and periodic objects like this reveal that the universe still harbours entire classes of phenomena we've yet to understand. The Milky Way, though familiar, continues to unveil secrets in wavelengths we're only now learning to hear. GLEAM XJ-6275 may just be the tip of the iceberg. Its return or the discovery of similar sources could open an entirely new field in astrophysics of compact objects. Until then, it remains a ghostly pulse from the silent depths of our own galaxy. In 2021, astronomers detected a neutron star displaying behaviour unlike anything seen before. It blinked in a seemingly chaotic pattern, emitting irregular signals reminiscent of cosmic Morse code. Named J0941+22, this star was observed producing intermittent radio bursts with no clear periodicity. Sometimes it fired off signals every few seconds, other times it went completely silent for hours or even days. This behaviour didn't fit into any known category. Traditional pulsars spin steadily, emitting regular lighthouse-like pulses. Magnetars can emit more erratic bursts, but usually tied to specific energetic events. J0941+22 followed neither a rhythmic pattern nor any physically detectable cycle. It seemed to operate on its own mysterious internal logic. Over a 6-month observation period, the star emitted hundreds of radio pulses, varying wildly in duration and strength. Some were short and faint, others long and intense. No repetition or mathematical sequence emerged, making it nearly impossible to model. Every attempt to predict its behaviour failed. Scientists classified the object as a long-lived radio transient, LRRT, a still poorly understood category in radio astronomy. These objects emit over extended periods but in irregular bursts. Very few confirmed examples exist, and none have been as active or unpredictable as J0941+22. It challenged everything we thought we knew about pulsar stability. One hypothesis is that J0941+22 is an extremely old neutron star with an unstable magnetic field and localized crustal collapses. These could trigger sporadic emissions as the magnetic field reorganizes. Another theory suggests it's accreting matter from an unseen companion, causing fluctuating electromagnetic interference. The fact that the star toggles between pulsar mode and complete silence suggests something is switching its emission mechanism on and off. This switch may be tied to internal conditions or external variations, but no orbital or environmental regularity has been found. The trigger remains a mystery. The emissions were recorded across both high and low radio frequencies, indicating a broad emission mechanism working in different atmospheric layers of the neutron star. Some pulses showed unusual dispersion and polarization, hinting at distorted magnetic fields or erratic plasma motion around the star. Adding to the intrigue, JEO 941 plus 22 was discovered by accident during a search for fast radio bursts, FRBs. Its detection supports the idea that the universe contains a much broader diversity of radio sources than previously imagined. It also shows that some stars may remain hidden for long periods, only revealing themselves during brief, unpredictable active phases. The chaotic blinking led to brief speculation about artificial origin. The Morse code comparison arose because the pulses varied in duration and were separated by pauses that seemed to suggest structure. However, statistical analysis found no recognizable coding. A natural but unknown origin is considered the most plausible explanation. Since then, telescopes like CHIME and LOFAR have continued to monitor the star in hopes of detecting long-term cycles or behavioral shifts. So far, JESO 941 plus 2 remains active in unpredictable bursts. Each new detection adds complexity to the dataset, but no physical model has yet successfully explained its erratic pattern. This kind of object raises new questions about neutron star physics and the role of magnetic instability in their behavior. There may be many more stars like JEO 941 plus 22 hiding behind long stretches of silence. Finding them will require patience, advanced algorithms, and constant monitoring of the radio sky. The star that blinks like a meaningless code may simply be exhibiting an extreme form of a still misunderstood phenomenon. Until its secret is uncovered, it stands as one of the most baffling examples of cosmic variability. In 2009, astronomers announced the discovery of a stellar mass black hole named LB1 that defied existing models of stellar evolution. This black hole, located about 15,000 light-years from Earth in the Milky Way, had an estimated mass of around 70 times that of the Sun, far larger than what current theories allowed for black holes formed from typical stellar collapse. According to conventional models, when massive stars explode as supernova, the resulting black hole should have a mass no greater than about 25 solar masses. Stars that would produce more massive remnants are expected to undergo pair instability supernovae, completely tearing themselves apart and leaving no core behind. The mass gap between 50 to 20 solar masses was considered off-limits for standard black hole formation. The black hole in LB1 seemed to violate that limit. It was identified through observations of a companion star orbiting an invisible object. By analysing the Doppler shift of the star's motion, astronomers inferred the presence of a massive companion, which had to be a black hole because there was no visible light. The orbital data suggested an astonishingly heavy black hole. The initial estimate of 70 solar masses generated shock and skepticism across the astrophysics community. If true, it would force a re-evaluation of how black holes are formed and how massive stars evolve. Some theorists proposed that perhaps the black hole formed from multiple mergers or in an environment with very low metallicity, allowing more mass to be retained after collapse. Others considered the possibility that the measurements were inaccurate due to angle-related effects in the orbit or misinterpretations in the spectral data. Further observations with additional telescopes and more refined models were conducted, and the mass estimate was revised. Some studies suggested values closer to 20 to 30 solar masses. Even so, LB1 remained unusually massive compared to other known black holes formed from single stars. Adding to the intrigue, the companion star in the LB1 system was also peculiar. It is a massive B-type star, and its proximity and orbital behaviour challenged assumptions about how such systems form. The pair may have undergone past interactions, such as mass transfer or common envelope evolution, further complicating the formation story of the black hole. Another hypothesis was that LB1 might actually be a binary black hole, and the companion star was interacting with two compact objects, not just one. This scenario could explain the high mass inferred from orbital dynamics, though no direct evidence of a second black hole in the system has been found. The idea remains under consideration, but requires further data. The discovery reignited interest in searching for more massive stellar black holes in our galaxy. It also highlighted the limitations of our current telescopic tools when it comes to interpreting indirect black hole signatures. While gravitational wave detectors like LIGO and Virgo detect collisions, Systems like LB1 offer a static snapshot of black hole behavior in binary environments. LB1 represents the growing realization that stellar remnants may be more diverse than previously thought. The discovery also spurred renewed modelling of low metallicity star populations, which might evolve differently and form heavier black holes. These environments are rare in our galaxy today, but were more common in its early history, perhaps pointing to ancient origins for such black holes. Whether or not LB1 has a 70 solar mass black hole, its existence has proven valuable in exposing gaps in our understanding of stellar death. It has helped refine the search methods for other massive black holes and encouraged the integration of data from radial velocity spectroscopy and gravitational waves. LB1 is no longer alone in its class, but it was one of the first to stand out. Since its discovery, LB1 continues to be monitored by ground-based and space telescopes. Variability in the light of its companion star and new spectroscopic data are helping constrain its parameters further. The system may also become a target for future X-ray and infrared missions, which could reveal more about the black hole's accretion behavior, if any. LB1 reminds astrophysicists that exceptions to the rule often hold the key to deeper understanding. Whether it truly broke the laws of black hole formation or merely exposed their edges, it remains a milestone discovery, a celestial oddity that pushed theory to catch up with observation. In 2020, the LIGO and Virgo gravitational wave detectors captured an event unlike any observed before. A merger between two black holes of unexpectedly large masses. The event, named GW 990521, involved black holes with masses estimated at 85 and 6 times the mass of the Sun, producing a final black hole of around 42 solar masses. This was the first direct evidence of an intermediate mass black hole. The detection shocked scientists because the larger black hole at 85 solar masses fell into the mass gap, a range where black holes were not expected to exist. According to theory, stars that would collapse into black holes in this range should instead explode in pair instability supernovae and leave no remnant. This made the 85 solar mass black hole theoretically impossible via single-star evolution. The collision produced the most massive black hole merger ever detected via gravitational waves. The signal lasted only 1/10 of a second, but carried enormous energy equivalent to about 8 solar masses converted into gravitational radiation. The resulting black hole fell into a previously unobserved range between stellar and supermassive black holes. Theories quickly emerged to explain how such black holes could exist. One hypothesis is that the 85 solar mass black hole was itself the result of a previous merger, a second-generation black hole. If true, this suggests that in dense environments such as globular clusters or galactic cores, black holes can collide repeatedly and grow through successive mergers. Another explanation involves primordial black holes formed shortly after the Big Bang from density fluctuations rather than stellar collapse. These hypothetical objects could occupy any mass range, including the gap, but there's no direct evidence they exist. GW 190521 revived interest in primordial black holes as a possible component of dark matter. The shape of the signal also surprised researchers. It had an unusually short duration and low frequency, indicating a nearly head-on collision rather than a spiraling-in spiral. This suggests the two black holes collided in a dynamic environment, possibly a dense star cluster or galactic nucleus, rather than slowly orbiting into each other over millions of years. This kind of direct plunge merger challenges previous assumptions about how black hole pairs form. Most known mergers involve black holes in long-lived binary systems. A chaotic dynamic origin like the one suggested for GW 990521 implies that black hole populations are more diverse and mobile than expected, especially in dense stellar environments. The final black hole at 42 solar masses is significant because it falls into the intermediate mass range, a class long theorized but only recently confirmed. These black holes could represent a missing link between the stellar mass and supermassive black holes found at galactic centers. Their detection opens new avenues for understanding black hole growth and galaxy evolution. GW 190521 also forced scientists to refine their gravitational wave models. The waveform was unusual and initially didn't fit templates based on known black hole masses and spins. It was only with flexible modelling and machine learning techniques that the signal was fully understood. This event expanded the boundary of what gravitational wave detectors are capable of identifying. The event's electromagnetic counterpart was uncertain. Some astronomers suggested a flare seen by the Zwicky Transient Facility could be linked to the merger, as the resulting black hole may have interacted with surrounding gas. However, the connection remained speculative. Most black hole mergers are believed to be dark with no light emission detectable. Since 2020, GW990521 has become a reference point for black hole astrophysics. It proved that the so-called mass gap is not a hard limit, but rather a theoretical frontier open to revision. Each new detection could push the boundaries further and reveal a continuum of black hole masses, bridging the gap between small and colossal. This detection helped confirm that black hole formation is not a one-size-fits-all process. Mergers, collisions, dense environments, and possibly early universe phenomena all play a role. GW990521 was not just an anomaly. It was a signal from the depths of space that our understanding of black holes is still in its infancy. In 2020, astronomers made a surprising observation: a possible flash of light that occurred in tandem with a black hole merger detected via gravitational waves. This was unexpected because black holes by nature do not emit light, especially not during collision. The event in question was GW990521, already notable for being a massive and unusual black hole merger. The flash was detected by the Zwicky Transient Facility, ZTF, in the same general location and time. The light burst was brief, lasting only a few days, and came from an active galactic nucleus, a region at the centre of a galaxy where a supermassive black hole is consuming material. Researchers proposed that the stellar mass black holes that merged may have been orbiting the supermassive black hole embedded in its accretion disk. When the two black holes merged, the resulting single black hole may have been kicked and interacted violently with surrounding gas. This interaction could have produced a shockwave or flare as the newly merged black hole ploughed through the accretion disk. The flash was consistent with a theoretical model where merging black holes within a gas-rich environment create electromagnetic counterparts. These light signatures would be incredibly valuable as they allow astronomers to study both gravitational and electromagnetic aspects of the same event. Such a multi-messenger detection, combining gravitational waves and light, is rare but scientifically profound. It allows for more precise localization of events and a deeper understanding of black hole environments. In this case, the light emission lagged slightly behind the gravitational wave detection, suggesting it may have been a delayed response to the merger itself. Timing and location correlations made it a compelling association. However, the evidence remains circumstantial. There's no definitive proof that the flash was caused by the merger. The region of space observed by ZTF is crowded with active sources, making it hard to confirm direct links. Nevertheless, the coincidence was strong enough to prompt deeper investigation and rethinking of how black holes might sometimes light up. This observation raised new theoretical possibilities. If black hole mergers occur in dense, gas-rich environments, they might frequently generate detectable light. That would challenge the previous assumption that black hole collisions are completely dark. Astrophysicists are now reworking models to incorporate gas dynamics, kick velocities, and shock propagation around merged black holes. There are also implications for future gravitational wave missions. Knowing that some black hole mergers might produce light means more coordinated sky surveys will be needed. Telescopes could be trained on predicted regions shortly after gravitational wave alerts looking for flashes, flares, or other transient events. This could vastly increase the scientific return from each detection. The flare observed after GW990521 was red and fading, matching theoretical predictions of a kicked black hole moving through dense gas. If confirmed, it would mark the first ever optical counterpart to a stellar mass black hole merger, something once thought impossible. This would represent a major breakthrough in understanding the environments where black holes reside. Not all black hole mergers would produce such flares. Events in empty space or low-density regions would remain dark, detectable only through gravitational waves. But in galactic nuclei or star-forming regions with thick gas disks, light emissions could be more common. Future detections will help determine how frequently this occurs. The potential for detecting both light and gravitational waves opens the door to precision cosmology. Distances can be calculated more accurately, and host galaxies can be identified. It also adds a visual dimension to an otherwise invisible cosmic phenomenon, helping bridge the gap between different fields of astronomy. The event encouraged collaboration between optical and gravitational observatories. It demonstrated the need for rapid response networks capable of scanning the sky within minutes of a gravitational wave trigger. The prospect of seeing black holes indirectly through their effects on surrounding matter represents a major shift in observational strategy. Whether or not this specific flash was caused by GW 190521, the event has pushed the boundaries of what we thought black holes could do. It suggests that even in the deepest darkness, under the right conditions, black holes might briefly shine, offering a fleeting but powerful glimpse into one of nature's most extreme processes, the black hole spinning near the limit of relativity. In 2023, researchers announced the observation of a supermassive black hole with a spin rate close to the theoretical maximum allowed by general relativity. This black hole, located in the galaxy MCG 063015, is spinning at over 90% of the speed of light. The measurement was made using X-ray spectroscopy, which detects how light is distorted as it escapes the intense gravity near the black hole's event horizon. Black holes can spin, and this spin is a key parameter alongside mass. In general relativity, the dimensionless spin parameter A ranges from 0, non-spinning, to 1, maximum theoretical spin. A black hole with a spin close to 1 is said to be extreme. This black hole's spin parameter was calculated to be greater than 0.98, placing it on the edge of what physics permits without violating relativity. High spin rates have profound implications. The faster a black hole spins, the closer the accretion disk can orbit without falling in. This increases the energy efficiency of accretion, meaning more radiation is emitted per unit of infalling mass. In practical terms, a maximally spinning black hole can convert up to 42% of infalling matter's mass into energy, compared to only 6% for a non-spinning one. The spin also affects the structure of space-time around the black hole. It causes a phenomenon known as frame dragging, where space itself is pulled around the black hole. This can lead to extreme relativistic effects such as the warping of orbits and the elongation of light paths. These effects were measured in the emitted X-rays, which were redshifted and broadened in predictable patterns. The data came from the XMM Newton and NuSTAR space telescopes, which observed iron K-alpha lines in the X-ray spectrum. These spectral features become distorted in the intense gravitational and magnetic environment near the event horizon. By modelling these distortions, astronomers can estimate the spin sin of the black hole with surprising precision. A spin so close to the limit raises questions about how such a black hole formed and evolved. It likely gained its spin from prolonged accretion of matter in one direction, possibly over billions of years. Alternatively, it may have merged with another massive black hole with a complementary spin. The black hole's extreme rotation tells a story of a long and violent cosmic history. There is a theoretical boundary beyond which a black hole cannot spin faster without violating the cosmic censorship conjecture or creating a naked singularity. The fact that this black hole remains within that bound suggests that general relativity is still holding up under the most extreme conditions, but the proximity to that limit makes it an ideal test case for future theories of quantum gravity. The observation also has consequences for jet formation. Many of the most powerful relativistic jets in the universe are launched from rapidly spinning black holes. The rotation powers magnetic fields and accelerates particles to near light speed. Although MCG 063015 does not currently host a large jet, its spin suggests it has the potential to do so under the right conditions. This measurement reinforces the idea that spin is one of the key drivers of black hole behavior. It affects how they grow, how they shine, and how they influence their host galaxies. Black holes with high spin may play a larger role in galaxy evolution than previously thought, especially through feedback mechanisms tied to radiation and outflows. Understanding extreme spin is also essential for interpreting gravitational wave signals. The spin of merging black holes alters the waveform shape and duration. Accurately measuring spin in astrophysical black holes helps refine models for LIGO and Virgo, improving our ability to infer the properties of distant mergers. The discovery continues to be refined as new data comes in. Future missions like Athena and XRISM are expected to provide even higher resolution X-ray spectra. These instruments will allow astronomers to probe deeper into the relativistic regions near black hole event horizons, offering a clearer view of the extremes of gravity. Black holes spinning near light speed aren't just fast. They're boundary-pushing laboratories of physics. By studying them, scientists are testing the very fabric of space-time. MCU 63015 may be just one of many black holes near the relativistic limit, but for now, it offers a rare look at what happens when nature operates at its absolute extremes. R36A1 is currently considered the most massive star ever observed in the universe. It resides in the R56 star cluster located within the Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Initial mass estimates placed R136A1 at around 320 times the mass of the Sun, though more recent calculations suggest it might be closer to 200 to 250 solar masses. Even at the lower estimate, it remains a record holder. The star is classified as a Wolf-Rayet star, a rare and extremely hot class of massive stars nearing the end of their short lives. These stars burn through their fuel at a ferocious rate and eject vast amounts of material via intense stellar winds. R136A1 is believed to be just a few million years old, but it's already shedding mass rapidly and could explode as a hypernova in the near future. Its size and mass challenge previously accepted upper limits for how massive a single star can be. Traditional models suggest that above about 50 solar masses, radiation pressure becomes so great that it halts further accretion of material. R136A1 appears to violate this limit, forcing astrophysicists to reconsider how massive stars form and evolve in dense stellar nurseries. One theory is that R136A1 formed through stellar mergers, the combination of two or more massive stars in a dense cluster. In these environments, close interactions and collisions are common, potentially leading to the formation of supermassive stars. This process may also explain the presence of other large stars nearby in the same cluster. The star's surface temperature exceeds 50,000 Kelvin, making it more than 8 times hotter than the Sun. Its luminosity is estimated to be several million times greater than that of the Sun. This intense brightness means it radiates enormous energy across the ultraviolet spectrum, ionizing the surrounding gas and contributing to the glow of the Tarantula Nebula. Despite its mass and energy output, R136A1 is difficult to observe directly due to its location. Its cluster is extremely crowded, and until recently, even the Hubble Space Telescope couldn't resolve it clearly. New observations from ground-based adaptive optics systems have helped refine measurements, but the exact parameters of the star remain under debate. The lifespan of R136A1 will be brief for stellar standards, likely no more than a few million years. It will likely end its life in a massive supernova or hypernova, potentially forming a black hole or even a pair instability supernova that leaves no remnant. If it does collapse into a black hole, it could be a significant contributor to gravitational wave events. The extreme mass of R136A1 also raises questions about the possibility of even larger stars existing in the early universe. When metallicity, meaning the presence of elements heavier than hydrogen and helium, was low, stars may have formed with much greater masses more easily. R136A1 could offer insights into what population 3 stars, the first stars in the universe, might have been like. Studying R136A1 helps refine stellar models by challenging our current understanding of radiation output, structure, and wind dynamics of such massive stars. This observation allows astronomers to test how light, matter, and gravity behave under extreme stellar conditions. The star's intense radiation not only impacts its immediate surroundings, but also affects nearby star formation. Its powerful winds compress gas clouds, triggering the formation of new stars, or conversely dispersing material and halting star formation altogether. As a result, R136A1 isn't just an anomaly. It plays a crucial role in shaping its local galactic environment. With the James Webb Space Telescope now operational, astronomers are eager to study R1b6a1 with even a greater detail. The infrared capabilities of the telescope will allow for better penetration of the surrounding dust and gas, giving scientists a clearer view of the star's mass loss rate and the surrounding nebula. This will refine our understanding of how such giant stars form and eventually die. For now, R136a1 continues to stand as a challenge to existing theories, a true marvel of nature, and a key to pushing the boundaries of stellar evolution. Whatever its eventual fate may be, it will continue to fuel astrophysical research and challenge our understanding of what stars can achieve. In astrophysics, the Eddington limit defines the maximum luminosity a star can reach before its own radiation pressure overcomes gravity, potentially tearing the star apart. If a star surpasses this luminosity, the outward force of photons should prevent further mass accumulation. Yet some stars, such as AG Carinae, seem to defy this limitation. AG Carinae is a luminous blue variable star, LBV, situated about 20,000 light-years away. It has a mass estimated at sub-T-solar masses, emitting light over 1 million times brighter than the Sun. During certain phases, particularly in outbursts, it temporarily exceeds the Eddington luminosity. However, rather than disintegrating, AG Carinae experiences episodic eruptions and sheds mass in enormous outflows, creating large shells of gas and dust visible through high-resolution imaging. This behavior implies that stars may possess mechanisms that allow them to temporarily defy the Eddington limit. Some astrophysicists suggest that instabilities in the star's outer layers permit energy to escape through narrow channels or bubbles, thus relieving internal pressure. This would enable the star to stay above the Eddington limit without losing cohesion. Another possibility is that rotation and magnetic fields could redistribute radiation unevenly, allowing the star to bypass this theoretical boundary. Other LBVs like AG Carinae and certain superluminous supernovae might maintain luminosities above the Eddington limit by rapidly shedding mass, or existing in a state of dynamic equilibrium, adjusting constantly to energy fluctuations. This possibility has profound implications for stellar evolution, especially regarding massive stars. If stars can exceed the Eddington limit, it may explain how they grow to such large sizes before eventually collapsing. This phenomenon could also be integral to the formation of massive black holes, particularly in the early universe, where stellar feedback played a role in shaping cosmic structures. AG Carinae offers astronomers an opportunity to observe these processes in real time. Telescopes such as Hubble and the James Webb Space Telescope are closely monitoring changes in its brightness, spectrum, and surrounding nebula. Through these observations, astronomers are refining models of radiation pressure, stellar winds, and internal convection. Interestingly, AG Carinae's eruptions are not periodic, with long stable periods followed by sudden bursts. This irregularity necessitates continuous monitoring to gather valuable data on how stars lose mass under extreme internal conditions. The possibility that stars might breach the Eddington limit also has significant consequences for understanding supernova progenitors. Many of the brightest supernovae ever recorded might have originated from stars in such a state shortly before their explosions. Recognizing the signs of such instability could help astronomers predict supernovae before they happen. Research also suggests that violations of the Eddington limit could be more common in low metallicity environments like those in early galaxies with fewer heavy elements, allowing stars to retain more mass and shine more brightly. Although the Eddington limit has been a cornerstone in astrophysical theory for nearly a century, stars like AG Carinae are now revealing its limitations. Nature often finds ways to circumvent theoretical boundaries, whether through rotation, magnetism, or structural complexity. By studying these massive luminous stars, astrophysicists continue to challenge their understanding of stellar behavior, black hole formation, and cosmic feedback mechanisms. In 2020, scientists reported an intriguing case of a neutron star that seemed to come back to life after a catastrophic event. This zombie star emerged following the merger of two neutron stars, an event first detected through gravitational waves as GW170817 in 2017. While most models predicted the formation of a black hole, strange signals suggested an alternate outcome. After the merger, a gamma-ray burst was observed, followed by long-lasting X-ray emissions. These X-rays persisted for weeks, defying expectations. If a black hole had formed immediately, the X-ray emissions would have faded quickly. Instead, the continued energy output indicated an object that persisted and continued to energize its surroundings. Some scientists proposed that the merger produced a massive neutron star, temporarily stable rather than a black hole. This neutron star would have been rapidly spinning with an extremely strong magnetic field, emitting energy through magnetar-like activity. This object would have been short-lived, teetering on the edge of gravitational collapse, but surviving due to its rotational energy. The idea of a zombie star challenged previous assumptions. It was believed that any neutron star formed from such a violent merger would immediately collapse. However, the zombie star model showed that high rotation rates and magnetic pressure could delay collapse, allowing the star to emit radiation and influence its surroundings before disappearing into a black hole. Numerical simulations supported this hypothesis, showing that high-density neutron stars could maintain temporary equilibrium under extreme conditions. These simulations matched the observed energy curves from the X-ray afterglow, and suggested that neutron stars might survive longer in low metallicity environments, where they could retain more mass post-merger. The implications of a zombie neutron star are far-reaching. It offers a new understanding of neutron star behavior, revealing a phase of matter supported by dynamic processes rather than structural integrity. Studying these objects helps physicists understand the equation of state for neutron star interiors, a key issue in high-energy astrophysics. Additionally, it challenges current models of short gamma-ray bursts and kilonovae, which are important for understanding heavy element formation in the universe. The prolonged energy output from the zombie neutron star could enhance the production of elements like gold and platinum compared to an immediate black hole collapse. Additionally, gravitational waves emitted during the delayed collapse could provide further insights into the star's rotation rate, internal structure, and other properties. Events like GW 170817 now stand as prime targets for future reanalysis, providing new opportunities to explore this mysterious phenomenon. The discovery of the zombie star also calls into question how we classify compact objects. Nature's actual complexity may extend beyond our simple binary neutron star or black hole framework, suggesting a broader spectrum of post-merger outcomes. As gravitational wave observations continue and new missions with improved sensitivity are launched, we may uncover more of these cosmic survivors. Until then, the zombie star remains a powerful reminder that cosmic death is not always the end. Rather than instantly collapsing, they might persist, rotating and shining, resisting collapse, if only for a brief moment. In 2018, astronomers made an astonishing discovery, a galaxy that appeared to lack dark matter. This galaxy, NGC 1052 DF2, is a diffuse object about 65 million light-years from Earth, and it immediately captured the scientific community's attention. Dark matter is thought to be an essential ingredient in galaxy formation, as most galaxies contain far more dark matter than visible matter. However, NGC 1052 DF2 didn't seem to adhere to this rule. The discovery was made using the Dragonfly telephoto array, a telescope designed to detect faint galaxies with low surface brightness. NGC 1052 DF2 looked unusually transparent, containing visible star clusters but exhibiting low overall mass. Measurements of the motion of these star clusters indicated that the galaxy's gravity could be explained entirely by its visible matter, implying little to no dark matter. This observation contradicted a fundamental concept in astrophysics, that dark matter serves as the gravitational glue that holds galaxies together. Normally, visible stars and gas make up only a small fraction of a galaxy's total mass, but in NGC 1052 DF2 the dynamics seem to match the mass of the stars alone. The absence of an invisible component raised major questions. Initially, some scientists questioned the accuracy of the distance measurement, suggesting that if the galaxy was closer, its mass would be lower, explaining the slower movement of the stars. However, follow-up observations using the Hubble Space Telescope confirmed the galaxy's distance and the anomaly. This led to more questions. Could NGC 1052 DF2 be the result of a tidal interaction with a larger neighbouring galaxy, like NGC 1052, which might have stripped the dark matter? Or perhaps it formed in a completely different way, possibly as a galaxy that never accumulated dark matter. Even more surprising was the later discovery of NGC 1052 DF4, a galaxy with similar characteristics, suggesting that NGC 1052 DF2 wasn't a unique case, but rather part of a new class of galaxies. These galaxies, deficient in dark matter, challenge the long-standing idea that dark matter is essential for a galaxy's structure and stability. One theory proposed that these galaxies could have formed from tidal debris in galaxy interactions, where gravity pulls streams of stars into new configurations, leading to the creation of star systems without dark matter halos. However, this hypothesis requires very specific conditions and doesn't fully explain the observed structure of NGC 1052 DF2 and NGC 1052 DF4. The debate has intensified as scientists questioned how these galaxies could remain stable without the gravitational support of dark matter. How have they avoided falling apart? Their stability suggests some compensating mechanism, such as high baryonic mass density, or interactions with surrounding intergalactic material. If these galaxies truly lack dark matter, they present a crucial test for dark matter theories. Models like modified Newtonian dynamics, MOND, which seek to replace dark matter with alternative theories, are challenged by the behaviour of NGC 1052 DF2. If gravity alone accounts for the motions of the stars here, but not elsewhere, this could suggest that gravity might be more complex or context-dependent. On the other hand, these galaxies might provide rare evidence that dark matter doesn't always accompany baryonic matter. If this is the case, NGC 1052 DF2 could be an exception that proves the rule, revealing how galaxies appear without dark matter, and why most galaxies differ. Telescopes like JWST and other upcoming observatories will offer better views of NGC 1052 DF2's internal dynamics, star populations, and surrounding environment. They could help determine whether the galaxy truly lacks dark matter, or if there's something we have missed. Regardless of the outcome, this galaxy is reshaping how we think about galaxy formation. In 2020, astronomers made a groundbreaking discovery of a galaxy called XM2599, a cosmic anomaly so massive and ancient that it defied the conventional timeline of galaxy evolution. Located around 12 billion light-years away, it existed when the universe was only 1.8 billion years old. What stunned scientists was the fact that XMM2599 had already stopped forming new stars, making it essentially a dead galaxy, even though it existed in an era known for rapid star formation. XMM2599 had a stellar mass exceeding 300 billion solar masses, which is more massive than our own Milky Way, which continues to form stars today. Yet, XMM2599 showed no signs of recent star formation, placing it among the quiescent galaxies, which are rare for such an early period in the universe's history. This led to the central question: how could such a massive galaxy form and exhaust its star-forming fuel so quickly? Several hypotheses were proposed. One possibility was that XMM2599 underwent an extremely rapid starburst phase, producing stars at an incredible rate early in its existence. Such intense activity could have depleted or expelled its gas, halting further star formation. This rapid depletion may have been triggered by mergers, black hole feedback, or violent interactions in a dense region of space. Another theory suggests that an active galactic nucleus, AGN, which could have been powered by a supermassive black hole at the centre, might have expelled the remaining gas, preventing further star formation. However, there is no direct evidence of an AGN in XMM2599. The existence of XMM2599 challenges expectations from the hierarchical structure formation model, which suggests that galaxies grow over time through mergers and accretion. XMM2599 appears to have skipped ahead, reaching maturity before most other galaxies had even formed. Its presence indicates that galaxy evolution may be more chaotic and diverse than previously thought. Moreover, XMM2599 does not fit the expected path of massive early galaxies, which are believed to evolve into brightest cluster galaxies, BCGs, in galaxy clusters. Instead, XMM 2599 remains isolated, leading to new questions about how galaxies transition between evolutionary states. The timing of the discovery is also crucial, as it coincides with the cosmic noon, a period when the universe was experiencing its highest rate of star formation. Finding a dead galaxy during this time suggests the presence of unknown quenching mechanisms that could stop star formation much faster than previously believed. Future missions, especially JWST, are expected to offer unprecedented insight into galaxies like XMM 2599. Its infrared capabilities will allow it to probe early cosmic dust, star populations, and black hole activity in greater detail than ever before. These observations may help determine if XMM 2599 is rare, or part of a hidden population of similar galaxies, and may ultimately change our understanding of early galaxy evolution. For now, XMM 2599 stands as a cosmic anomaly, a giant that formed too quickly, burned brightly, and then went silent in a universe just beginning to take shape. It offers a glimpse into the diversity of galaxies and challenges our understanding of cosmic development. Another factor that could contribute to the formation of spiral galaxies without the need for galactic collisions may be internal gravitational instabilities. These instabilities can occur in dense, rotating disks, and might have been more common in the early universe due to high gas fractions. They would have allowed spiral structures to form earlier than expected, enabling the self-organization of galaxies. The presence of ordered rotation in such a young galaxy also sheds light on how angular momentum was acquired in the early cosmos. If galaxies like BRRI 135041 retained their spin during formation, it suggests that tidal forces and inflows played crucial roles. These mechanisms may have been key in shaping early spiral galaxies in ways that we are only beginning to understand. Spectroscopic measurements of carbon and other emission lines were used to confirm the galaxy's redshift and age. These lines provided insights not only into the galaxy's age, but also into its metallicity and star formation rate, which were surprisingly high. This indicates that BRRI 135041 was not only structurally organized but also chemically evolved, even at such an early stage in the universe. This discovery hints at the possibility of a new class of primordial spirals, massive gas-rich galaxies that assembled quickly and formed disks early. If more such galaxies are discovered, astronomers may have to reconsider the timeline and processes behind the formation of spiral arms, possibly incorporating new physics related to gas cooling, turbulence, and feedback. The discovery also addresses the mystery of why spiral galaxies are so common today. If spiral structures can form quickly, they may have always been favoured under certain conditions, helping to explain their prevalence in the local universe without requiring complex transformation processes over billions of years. Future observations using the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, could reveal more about the internal dynamics of BRRI 135041, especially by resolving individual star-forming regions and comparing them to simulations. Scientists hope to pinpoint the exact conditions that allowed spiral arms to form so early. For now, this distant spiral galaxy serves as evidence that order emerged much earlier in the universe than previously thought. Its elegant shape, formed in the chaos of the early cosmos, challenges our understanding of cosmic time and structure, suggesting that the universe may have settled down far sooner than we once believed. In recent years, astronomers have uncovered an unexpected phenomenon. The axes of rotation of galaxies billions of light-years apart appear to be aligned. This contradicts the assumption that on cosmic scales, galaxy orientations should be random due to the chaotic nature of their formation. This discovery was made by studying the polarization of light from distant quasars, which are extremely bright active galactic nuclei. In the 2000s, a study led by Damien Hutzemarkers used the Very Large Telescope VLT to measure light from over 300 quasars. They found that the polarization vectors of these objects, essentially the direction in which their light waves oscillate, showed coherent alignment over regions of space spanning more than 1 billion light-years. This alignment stands out when compared to what random distributions would produce. The findings suggest that the spin axes of galaxies, or their central black holes, may be oriented in roughly the same direction across vast cosmic expanses. The effect was observed at redshifts greater than 1, meaning the light originated when the universe was less than half its current age. This makes the alignment a relic from the early universe. One proposed explanation is the influence of cosmic filaments, massive thread-like structures of dark matter and gas that connect galaxies. Galaxies forming within the same filament might have acquired spin from the same gravitational dynamics, leading to parallel orientations. However, the alignment zones observed are much larger than expected from these filamentary structures. Another possibility is that a primordial magnetic field, which permeated the early universe, could have influenced the angular momentum of forming galaxies. Yet current observations of the cosmic microwave background, CMB, do not support the existence of such a pervasive field with sufficient strength, leaving this idea speculative. Some theorists have suggested even more exotic possibilities, including the hypothesis that the alignment hints at anisotropies in the fabric of space-time that could violate the cosmological principle, an assumption that the universe is isotropic and homogeneous on large scales. If this principle doesn't hold, it could mean a fundamental shift in our cosmological models. The effect might also be linked to cosmic inflation, the rapid expansion of the universe after the Big Bang. If inflation introduced slight directional biases in the quantum fluctuations that seeded cosmic structure, it could help explain large-scale alignments today. However, the mechanics of such a connection remain unproven. Skeptics argue that the observed alignment might be a statistical fluke, or the result of biases in how light polarization is affected by intervening matter and magnetic fields. But multiple studies with different datasets have found similar results, reducing the likelihood that it's just an observational artifact. More recent surveys, including those from SDSS and GAA, have corroborated some of these findings, though they also highlight the complexity of analyzing galaxy spin directions and light polarization over such vast distances. Improvements in data quality and larger sample sizes are crucial for confirming the alignment. If confirmed, it could reveal a hidden large-scale structure or pattern in the universe, something that goes beyond current models of cosmic evolution. It might influence our understanding of the roles of the initial conditions, dark matter, and dark energy in shaping the cosmos. It could even point toward new physics. Future telescopes such as the Square Kilometre Array, SKA, could map galaxy spins and polarizations across billions of light-years with unprecedented precision. These observations may finally settle whether these alignments are real and, if so, what they truly mean. Until then, the mystery of aligned galaxies remains an intriguing puzzle written across the cosmos. For now, the anomalous spin alignment serves as a tantalizing clue that the universe may still hold large-scale patterns we have yet to understand, a quiet echo of cosmic structure imprinted on the grandest scales. The cosmic microwave background, CMB, is the afterglow of the Big Bang, a faint radiation field that fills the universe. In theory, it should be statistically uniform, showing only tiny fluctuations resulting from early quantum variations stretched by cosmic inflation. However, in the early 2000s, data from WMAP and later the Planck satellites revealed a troubling anomaly, a strange alignment of low-order moments, which became known as the axis of evil. This term, partly coined in jest, reflects a serious scientific phenomenon. It refers to the alignment of the quadrupole and octupole moments, large-scale temperature patterns in the CMB along a common axis. These alignments are not predicted by the standard cosmological model, which assumes that such features should be isotropic and randomly distributed. The alignment appears to point roughly toward the constellation Virgo, and it is uncomfortably close to the plane of the solar system, the ecliptic. This has raised questions about whether the anomaly is due to foreground contamination or a systematic error in data processing. Despite repeated cleaning and cross-checking, the effect has not been eliminated. If the alignment is real, it would challenge the cosmological principle, which asserts that the universe is the same in all directions on large scales. The axis of evil suggests that the early universe may have had a preferred direction, contradicting our current understanding of inflation and homogeneity. Some physicists have speculated that topological defects like cosmic strings or domain walls, left over from phase transitions in the early universe, could be the cause. Others have proposed more speculative explanations, such as the influence of multiverse collisions or the possibility that our universe is embedded in a larger anisotropic structure. Another theory suggests that non-trivial topologies, such as a universe shaped like a torus or with wraparound geometry, might account for the large-scale directional bias. These models often predict repeating patterns or alignments, and the axis of evil could point toward them. However, no such geometry has been confirmed. Skeptics argue that the alignment is statistically marginal and it may just be a coincidence, amplified by our natural tendency to find patterns. The likelihood of such an alignment occurring by chance is low, but not impossible. Some believe that future CMB surveys will show the anomaly to be a statistical fluke. Still, the anomaly persists across multiple missions. The Planck satellite, with higher resolution and better noise control, confirmed the same alignment. This strengthens the case that the axis of evil is not just an artifact of WMAP or data processing techniques. If real, this alignment could impact our understanding of inflationary models and the calibration of fundamental constants. It might even necessitate a revision of standard cosmology, incorporating early universe dynamics that favored certain directions, a profound shift in our view of the cosmos. The axis of evil also has philosophical implications. If the universe has a preferred direction, it would make our location and orientation within it less arbitrary. This would revive ancient questions about cosmic structure and human perspective now backed by precision data. Future missions like the proposed Lightbird satellite aim to map the CMB polarization with even greater sensitivity. If the axis of evil is confirmed, it could mark the beginning of a new era in cosmological theory, where randomness no longer dominates our understanding of the universe's creation. Until that time, the axis of evil remains one of the most captivating cosmic puzzles, a quiet but consistent suggestion that the universe may be far more structured and perhaps even more intentional than we ever thought. One of the most extraordinary discoveries in recent years is the Hercules Corona Borealis Great Wall, a colossal structure that challenges everything we know about the universe's large-scale organization. Discovered in 2013, this immense cluster of galaxies, gas, and possibly dark matter spans across an astonishing 10 billion light-years. Known as the Hir-CRBG, it is the largest known structure in the observable universe by a wide margin. This discovery was made through observations of gamma-ray bursts, GRBs, which are among the brightest phenomena in the universe. By mapping the positions and redshifts of these bursts, researchers noticed a surprising concentration of them in one specific area of the sky, indicating a vast clustering of galaxies. The structure appears so large that it contradicts the cosmological principle, which assumes that matter in the universe is spread out more evenly at the largest scales. The Great Wall spans a remarkable 10% of the observable universe's diameter, and such an immense structure should not exist according to current models of cosmic expansion and dark energy. The size of this wall raises fundamental questions about how the early universe formed structures and whether our models of gravitational clustering and dark matter interactions are sufficient. Some scientists argue that this structure is not a singular wall, but a collection of loosely connected galaxies that appear continuous from our perspective. Yet even this interpretation presents challenges, as simulations suggest that such large-scale alignments are rare. Other researchers suggest that this anomaly could point to non-standard cosmological models, such as anisotropic expansion, where the universe expands at different rates in different directions, somewhat like the effect seen in the axis of evil. These findings, when combined with others like the Sloan Great Wall and the Large Quasar Group, indicate that the complexity of the universe's evolution might be far more intricate than we once believed. Importantly, the structure is not gravitationally bound, meaning that over time the expansion of the universe will cause parts of the Great Wall to drift apart. However, the fact that it emerged from a relatively dense region of the early universe suggests that there could be a shared origin or process that caused such large-scale clustering. To better understand the nature of the Hir-CRBG, astronomers are now using deeper surveys with tools like the Vera Rubin Observatory and Euclid. to map out more detailed galaxy distributions. These future observations could provide crucial insight into its formation and significance. The Great Wall serves as a powerful reminder that while the universe is expanding, its largest structures may still challenge the theoretical boundaries we've constructed. It may not just be a vast collection of galaxies, but a testament to the limitations of our understanding. Another cosmic anomaly that challenges our understanding is the cold spot in the cosmic microwave background, CMB. The CMB is the faint radiation leftover from the Big Bang, and it offers us a snapshot of the universe just 30,000 years after its birth. While the CMB is mostly uniform, it contains small fluctuations, ripples that set the foundation for all cosmic structure. Among these fluctuations is the mysterious cold spot, first detected in data from the WMAP satellite and later confirmed by the Planck satellite. This cold spot, located in the southern hemisphere of the sky, exhibits temperatures about 70 microkelvins lower than surrounding areas, a temperature anomaly that standard models of cosmology can't easily explain. The cold spot's persistence across multiple datasets makes it a real anomaly rather than a statistical outlier. Some theorists have proposed that the spot is the result of photons losing energy as they pass through a large cosmic void, like the Eridanus supervoid. But whether this void is large enough to account for the anomaly is still debated. Other explanations have suggested that the cold spot could be a result of an early phase transition in the universe, such as a domain wall, or even a sign of a collision with another universe, a bruise left by a neighbouring bubble in a multiverse scenario. However, these theories are speculative, and the true origin of the cold spot remains elusive. If the cold spot is indeed real and not just a statistical fluke, it could offer insights into pre-inflationary physics, a time before the rapid expansion that smoothed out most of the universe's irregularities. It could be a clue to the dynamics of the early universe, or even a link between inflation and quantum gravity theories. Upcoming missions like Lightbird and CMB-4 will provide more detailed views of CMB anomalies and may shed light on the origin of the cold spot. Until then, the cold spot serves as a persistent reminder that the universe still holds mysteries we have yet to fully understand. The IceCube Neutrino Observatory in Antarctica offers another fascinating window into the cosmos. This detector, embedded deep beneath the Antarctic ice, has detected high-energy neutrinos, ghostly particles that travel across the universe unimpeded by matter or magnetic fields. These neutrinos carry energy beyond what is typically expected from known astrophysical sources, suggesting they originate in extreme environments like black holes, quasars, or gamma-ray bursts. While some neutrinos were traced back to known blazars, others seem to come from random directions with no apparent source, hinting at unknown cosmic accelerators or physics beyond the standard model. IceCube's ability to detect these elusive particles relies on over phasm light sensors buried deep in a cubic kilometre of ultra-pure ice. When a neutrino interacts with a nucleus in the ice, it produces a faint flash of light, which the sensors pick up. This allows scientists to track the neutrino's path and energy, revealing more about the most energetic processes in the universe. These neutrinos' random origins and high energies make them a mystery, challenging our understanding of cosmic accelerators. The fact that we can detect them at all is a testament to the power of the IceCube Observatory, but the true origins of some of these particles remain one of the universe's most puzzling questions. One of the most puzzling phenomena is the absence of electromagnetic signals accompanying some of the most energetic neutrinos detected, including one known as Big Bird. These neutrinos appear with no visible counterpart, no light, no X-rays, no gamma-ray bursts, nothing. This creates a major challenge for models that associate neutrino production with bright, violent cosmic events. Could these neutrinos originate from a completely new class of dark objects or something far more exotic? Some theorists suggest that these neutrinos might be the byproducts of decaying dark matter, where large, heavy particles slowly disintegrate over time, releasing neutrinos as one of the few detectable signs of their existence. If this theory holds, IceCube could be witnessing not just cosmic events, but hints of dark matter behaviour at the edge of the known universe. Others propose more unconventional ideas, such as sterile neutrinos, hypothetical particles that interact even less than standard neutrinos and could connect with theories involving higher dimensions. The detection of these strange fluxes and energy levels could indicate that IceCube is detecting entirely new particles, potentially revolutionizing our understanding of the universe. Adding to the intrigue, some of these neutrinos seem to be coming up through the Earth, suggesting they entered from the northern hemisphere and travelled through the planet before being detected. This trajectory eliminates many terrestrial sources and confirms their extraterrestrial origin. IceCube's neutrino map is still a work in progress, but it is steadily revealing a layer of the universe that no telescope can directly observe. Neutrinos provide a glimpse into the deepest, most energetic processes of the cosmos, events that leave little to no electromagnetic signature. Future upgrades to IceCube, such as the IceCube Gen 2 project, aim to increase its sensitivity and detection volume, with better coordination with optical, X-ray and gravitational wave observatories. These improvements might help scientists match these ghostly neutrinos to their cosmic sources, or confirm that they arise from entirely unknown origins. Whether they are produced by dark matter, distant cosmic entities or new physics, the neutrinos detected beneath the Antarctic ice are messages from the universe's most hidden corners. They pass through us in silence but could carry answers to questions we haven't even learned to ask yet. The cold dark matter theory is the leading model for understanding how structure forms in the universe, predicting the hierarchical formation of galaxies, with smaller dark matter halos merging to form larger galaxies. According to this model, there should be hundreds or even thousands of tiny dwarf galaxies surrounding large galaxies like the Milky Way. However, astronomers have observed far fewer dwarf galaxies than the model predicts. This discrepancy, known as the missing satellite problem, highlights a major conflict between theory and observation. While the cold dark matter model expects hundreds of dwarf galaxies, only a few dozen have been detected, many of which are barely visible. One possible explanation is that dwarf galaxies are faint, diffuse and difficult to detect. Their stars are sparse and they emit very little light. Some recent surveys, particularly those using gravitational lensing and deep photometry, have uncovered more faint galaxies, but still not enough to match the predictions of the cold dark matter theory. Another theory suggests that many of the small dark matter halos never formed stars at all. These dark dwarf galaxies would be invisible through traditional telescopes, but might still exert gravitational influence on their environment. Proving the existence of galaxies that emit no light would be extremely difficult, but it remains a possibility. Some researchers have proposed that stellar feedback from supernovae or stellar winds could have expelled gas from small galaxies early on, preventing star formation. If true, this would mean that many dark matter halos were effectively sterile from the very beginning of their existence, creating a hidden population of dead dwarf halos. Other researchers challenge the cold dark matter model itself, proposing alternatives such as warm dark matter or self-interacting dark matter. These models suggest that lighter, slower or more interactive dark matter particles could explain the smooth distributions observed in the universe today. Simulations based on cold dark matter are improving in resolution and incorporating more realistic physical models, such as gas cooling, star formation and feedback. While these simulations have narrowed some of the discrepancies with observations, the problem remains, particularly in our galactic neighbourhood, the local group. One promising approach to detect these invisible dwarfs is gravitational lensing, where slight distortions in the light from distant galaxies can reveal unseen mass. Future telescopes such as the Euclid and the Nancy Grace Roman telescope will provide new data sets that may help confirm or refute the existence of these dark dwarf galaxies. Meanwhile, surveys like Gaia are uncovering more ultra-faint galaxies surrounding the Milky Way, suggesting that we're still missing many of the faintest members of this population. The question of whether these missing galaxies are invisible or never existed at all could reshape the foundations of cosmology. In 2016, astronomers discovered a galaxy called Dragonfly 44 that is composed almost entirely of dark matter, 99% to be exact. Initially, this galaxy was thought to be a faint, diffuse blob, but upon further examination, it became clear that its stars were moving much faster than expected for such a faint galaxy. This suggested the presence of a massive, invisible component holding the galaxy together, dark matter. Dragonfly 44 is classified as an ultra-diffuse galaxy, UDG, a type of galaxy that is as large as the Milky Way, but with far fewer stars. This galaxy challenges our assumptions about galaxy formation and evolution. In standard models, dark matter acts as the scaffolding for galaxy formation, and visible matter follows. However, Dragonfly 44 has only 1% of the visible matter that the Milky Way contains, yet it has a mass nearly equal to the Milky Way, suggesting that dark matter plays a dominant role in holding it together. The galaxy also contains an unusually high number of globular clusters, which are thought to form in the early universe, further supporting the idea that Dragonfly 44 formed in a massive dark matter halo, similar to larger, brighter galaxies. Dragonfly 44's existence raises questions about how it managed to form with so few stars. Did it lose its gas early in its history, or was there some feedback mechanism, such as supernova explosions or an active black hole, that prevented further star formation? The discovery also suggests that there may be many more such galaxies hidden in the cosmos, too dim to detect with traditional methods. If a population of ultra-diffuse galaxies with a high dark matter content exists, it could have significant implications for our understanding of mass distribution in galaxy clusters. Dragonfly 44's existence also provides a unique opportunity for testing dark matter theories. If alternative gravity models, such as modified Newtonian dynamics, MOND, are correct, then galaxies like Dragonfly 44, with so few stars but such strong internal gravity, should not behave the way they do. The galaxy's dynamics aligning with dark matter predictions strengthens the case for its existence. Although there have been some revisions to its mass calculation, Dragonfly 44 remains an extreme case of a dark matter-dominated system. As new telescopes like the James Webb Space Telescope, JWST, and the Vera Rubin Observatory continue to probe the universe, they may uncover more galaxies like Dragonfly 44, allowing us to better understand ultra-diffuse galaxies and the role of dark matter in their formation. Dragonfly 44 serves as a ghostly giant, massive yet nearly invisible, silently orbiting in the cosmos. Its existence not only confirms the role of dark matter, but also reminds us that the universe is still largely made up of what we cannot see. The cosmological constant, also known as lambda, plays a pivotal role in the equations of general relativity, representing the energy density of empty space or dark energy. Initially introduced by Einstein to keep the universe static, lambda was discarded after the discovery that the universe was expanding. However, in the late 1990s, observations of the accelerating expansion of the universe brought the cosmological constant back into prominence. Today it is considered the simplest explanation for the universe's accelerated expansion. The problem, however, is staggering. Theoretical predictions for the vacuum energy from quantum field theory yield a value for lambda that is 10 or 20 times greater than what is observed. This represents the largest discrepancy between theory and observation in all of physics. Observationally, lambda is incredibly small but not zero. It is just large enough to dominate the expansion of the universe, but why it is so small remains one of the greatest unsolved mysteries in cosmology. If the cosmological constant were even slightly larger, galaxies would have never formed. On the other hand, if it were smaller, the universe might have collapsed. Its precise value appears to be finely tuned, and this has led to what's known as the cosmological constant problem. This is one of the most perplexing issues in theoretical physics. Why is the energy of empty space so small but not zero? And why does it only become significant 13.8 billion years after the Big Bang? Some physicists speculate that this is simply a cosmic coincidence, that we are just living in a narrow time frame when the cosmological constant becomes relevant. Others suggest the anthropic principle, which argues that we observe this value because only a universe with such a small cosmological constant could harbour observers like us. Another possibility is that the cosmological constant might not actually be constant. This has led to theories of dynamic dark energy such as quintessence, where dark energy changes over time. However, current observations still support the idea that it is a true constant, and until measurements become more precise, this remains a speculative theory. Theoretical frameworks, including string theory, propose the existence of multiple universes with different values of the cosmological constant, essentially a multiverse. In this view, we live in a universe where the cosmological constant is small enough to allow galaxy formation. However, such ideas are difficult to test directly and remain controversial. Physicists have also explored modified gravity theories that aim to eliminate the need for the cosmological constant by altering how gravity functions on cosmic scales. These theories include vigravity, mass gravity, and other extensions of general relativity. So far, none have displaced the cosmological constant as the best explanation based on observational data. Despite its minuscule value, the cosmological constant still dominates the universe's energy budget today, contributing around 70% of all mass energy. It drives cosmic acceleration, impacts structure formation, and dictates the future of the universe, likely leading to eternal expansion and a cold, dark end. The underlying issue, however, is why the vacuum energy, predicted by quantum physics to be enormous, has such a minuscule effect in reality. This discrepancy highlights the deep incompatibility between general relativity and quantum mechanics, and it might require a unified theory of quantum gravity to resolve. Upcoming surveys, such as those from the Euclid, DC, and Roman Space Telescope, will examine the universe's expansion history in finer detail. They could provide crucial insights into whether dark energy evolves or remains constant. Any deviation from the expected behavior could offer significant information about the true nature of the cosmological constant. Until then, the cosmological constant remains a silent force ruling the cosmos. Its infinite decimal value is simple in form yet profoundly mysterious. It's a quiet whisper in Einstein's equations, and possibly the universe's greatest secret. Another enigma in cosmology is the missing lithium in the primordial universe. According to the Big Bang theory, the abundance of light elements, hydrogen, helium, and a small amount of lithium, formed in the first few minutes of the universe's existence, in a process known as Big Bang nucleosynthesis, BBN. While the predicted amounts of hydrogen and helium match observations well, the lithium levels are consistently lower than expected. Specifically, BBN models predict about 3 times more lithium-7 than we observe in the oldest stars, known as population 2 stars. These ancient stars, formed shortly after the Big Bang, should serve as time capsules for studying early element abundances. The unexpectedly low lithium content in these stars has become known as the cosmic lithium problem. Several explanations have been proposed to solve this. One idea is that lithium was destroyed inside stars after their formation, but this would require an unreasonably uniform process across many stars, which seems highly unlikely. Another theory suggests that lithium was never fully formed due to conditions that deviated slightly from the predictions of BBN. Some particle physics models propose the involvement of unknown processes or particles, like the decay of supersymmetric matter during or after BBN. These hypothetical processes could have altered nuclear reaction rates, leading to lithium's destruction before it could be trapped in stars. A third possibility is that early universe physics was different from what we assumed, perhaps involving time-varying constants or additional neutrino species that changed the thermal history. These speculative changes could explain the lower lithium yield without affecting hydrogen and helium predictions. New data from large sky surveys and high-resolution spectroscopy continue to confirm the low abundance of lithium, reinforcing the idea that the issue is not just observational bias. In addition to lithium-7, there's a discrepancy in lithium-6, a rarer isotope. BBN predicts virtually none of it, but small amounts appear in stellar atmospheres. If these detections are real and not artifacts, it suggests additional non-BBN nuclear processes, potentially involving cosmic ray interactions or exotic physics in the early universe. Some researchers have also questioned the reliability of using stellar atmospheres to measure primordial lithium, proposing that lithium may be buried deeper inside stars due to gravitational settling or turbulent mixing. Even with this consideration, the full discrepancy remains unexplained. The lithium problem remains one of the most significant gaps between theory and observation in standard cosmology, urging a re-evaluation of our assumptions about the early universe. Future observations from the James Webb Space Telescope and ongoing experiments in nuclear astrophysics may help refine our understanding of primordial element formation. Until then, the missing lithium remains an anomaly, quietly hinting at overlooked astrophysics or pointing toward new physics waiting to be uncovered. Solving this mystery could provide a deeper understanding of how the universe began, evolved, and formed its first stars. Finally, the Hubble constant, HU, which describes the rate of the universe's expansion, is one of the most important numbers in cosmology. It is essential for determining the universe's age, size, and future. However, in recent years, a major problem has emerged. Different methods of measuring HLRO yield inconsistent results, and the discrepancy is too large to ignore. When measured using local observations like Cepheid variable stars and Type 1a supernovae, the Hubble constant is about 7374 kmS per megaparsec. But when measured indirectly through the cosmic microwave background, CMB, assuming the lambda-cold dark matter LCDM model, it is closer to 768 km per megaparsec. This discrepancy, known as the Hubble tension, has become one of the most urgent puzzles in astrophysics. One possible explanation is that there may be a systematic error affecting one or both of the measurement methods. However, multiple independent studies using different telescopes and techniques have confirmed both high and low values. Each method is internally consistent, but they are mutually incompatible. Other ideas suggest that new physics might be at play between the early and late universe. For instance, adding a new component to the universe's energy budget, such as early dark energy or decaying dark matter, could reconcile the difference. These changes would affect how the universe expanded during its first few 100,000 years. Some models even propose that the cosmological constant may not be constant, or that dark energy began influencing expansion earlier than we previously thought. Other radical theories suggest that the Hubble constant may not be constant at all, but might vary depending on location or direction, challenging the cosmological principle, which assumes that the universe is the same in all directions. The Hubble tension also raises important questions about the age of the universe. A higher HO implies a younger universe, potentially hundreds of millions of years younger than the age inferred from the CMB. This discrepancy could have significant implications for the formation of the first galaxies and stars, and for the evolution of cosmic structures. To resolve this issue, astronomers are turning to gravitational wave events from neutron star mergers as a new kind of standard siren. This innovative approach may help determine if there is new physics at play, bridging the gap between the early and late universe. Until more precise measurements are made, the Hubble tension remains a central focus in cosmology, offering the potential for breakthroughs that could radically change our understanding of the universe's expansion. Upcoming missions like Euclid, Nancy Grace Roman Telescope, and CMBS-4 aim to improve measurements of the universe's expansion. These may either narrow the gap in the Hubble constant debate or reveal new physics. Currently, the Hubble tension is a cosmic puzzle, with two robust methods pointing to different conclusions. Resolving it could lead to breakthroughs or show flaws in existing models. Quantum vacuum isn't truly empty. Quantum field theory tells us that it's a sea of virtual particles, constantly appearing and vanishing. This activity influences the structure of the universe, particularly in dark energy, which accelerates cosmic expansion. At quantum levels, space is filled with fields like the electromagnetic and Higgs fields, even in the lowest energy states. The vacuum could have structures, like crystal lattices, and some theories suggest hidden dimensions or symmetries. This challenges the classical view of vacuum as nothing. Quantum vacuum might even explain the universe's creation, possibly emerging from a fluctuation in an empty vacuum. This opens philosophical debates about whether nothing truly exists in physics, as instruments always detect something even in the void. In quantum mechanics, the vacuum can create virtual particle pairs that alter real particles' behavior. This shows that the vacuum has real effects, not just theoretical ones. Black holes are another mystery. What happens to information that falls into them? The black hole information paradox arises because quantum mechanics says information cannot be destroyed, but general relativity suggests it's lost once past the event horizon. Various theories try to resolve this, such as encoding information in Hawking radiation or on the event horizon. Others propose firewalls or black hole complementarity, but these ideas remain speculative. New calculations suggest information may escape through Hawking radiation after a black hole's evaporation reaches a certain point. The search for a quantum gravity theory may solve this paradox, but it remains unsolved. Finally, Saturn's hexagonal storm is a striking feature visible for decades. The storm's stability and sharp edges challenge atmospheric dynamics. It's thought to form due to differential rotation in Saturn's atmosphere, where winds move at different speeds at various latitudes. This forms stable wave patterns. At the storm's centre lies a massive vortex with wind speeds over 500 km. Unlike Earth's storms, it stays fixed at the pole. The lack of a similar hexagon at Saturn's south pole adds to the mystery, suggesting the storm may depend on unique conditions in the north. The storm's structure and behaviour continue to puzzle scientists, revealing a fascinating aspect of Saturn's atmospheric complexity. Saturn's hexagonal storm is a massive spinning pattern that challenges our understanding of weather. It's more than just a surface pattern. It's likely a vertical vortex, like an atmospheric wave. Over Cassini's 13-year mission, scientists saw the hexagon change colour from blue to gold, likely due to sunlight's effect on Saturn's atmosphere. This unique storm continues to puzzle scientists, showing us how even chaotic weather can form distinct, stable patterns. It's a reminder that nature can create order where we expect disorder. Enceladus, a moon of Saturn, also revealed surprising activity. It has cryovolcanoes that eject water and ice from deep fractures at its south pole. These eruptions are fueled by a liquid water ocean beneath its icy surface, warmed by Saturn's gravity. This discovery raises the possibility that Enceladus could harbour life, as it contains water, organic compounds, and hydrogen, a key element for life. The consistency of these eruptions suggests that Enceladus could be a dynamic, habitable world despite its icy exterior. Astronomers also suspect the existence of a ninth planet in our solar system. This planet 9, if it exists, would be much farther than Neptune, orbiting at distances between 400 to 800 AU. Its gravity may be responsible for the unusual orbits of distant objects. Though no telescope has spotted it yet, evidence continues to build. If Planet 9 is real, it could reshape our understanding of planetary formation. Some believe it could be a rogue planet or one that was ejected during the solar system's early years. For now, Planet 9 remains a mystery, but with promising clues pointing to its existence. If you genuinely enjoyed this content, don't forget to hit that like button and subscribe for more amazing videos. Your support helps us bring you more exciting discoveries. Good night.